Alright everyone, so we're doing physics, and math now. And we're actually going to start with the chapter 10 section, CH10. Oh, my writing's not too great. Let me get the pen out. You know it's serious when we get the pen out because now we're going to do lots of learning. So yeah, chapter 10 on mathematics. And the reason why I'm going over mathematics first is because obviously if you're struggling with your math, then doing basic physics problems will be difficult. I'm not sure why in the textbook they kind of stuffed it at the back as a second thought. My thought is probably because the textbook is made for specifically premeds who have had basic exposure to math and are able to do these approximations. So if you're already like a pre-med really good at that, that's fine. You can just skip ahead. But you know, review for any skill level is a good review because you know you never know when you might learn something new, I guess. Yeah, I'm gonna do this on the whiteboard now. So what I'm gonna show you is first about scientific notation. Again, if you're a pre-med that knows, you know, your math already, then you can skip ahead. But this is for a lot of beginners as well, because I assume a lot of people on the internet might be beginners. So I like to start from the foundation up. And one of your foundations doing physics is doing math, and then physics. And then on top of that is then doing the questions. You've memorized all the formulas and stuff like that. Okay, so whoa, is it grabbing this? Okay. So first we're going to go over arithmetic and significant figures. This is just right here on chapter 10. So I just copied it on this whiteboard, so for reference for me, but also for you to see and follow along with the regular Meltdown handout. So first we're starting off with scientific notation. So I'm going to do it in yellow. Scientific notation. And the first thing you want to learn is how do you get a number to be in scientific notation. So I'll give my own examples. They won't be the best at the top of my head, but let's say I have 600. That's one of them that I'm going to do. And then I'm going to do 324, 0. Okay, so these are the numbers that I want to convert into scientific notation. Now, what you're going to do is you're going to need to know the Lars method as well. So this Lars mnemonic here. So I'm going to show it from here because it's more higher quality. So this Lars mnemonic is important because it'll tell you where you're going to move the decimal with scientific notation. So if you move to the left, you're adding, but if you move to the right, you're subtracting. And you'll see this in a second. So if I move this decimal to the left, then I'm adding more of this exponent, right? So 7 plus 2 places, 7 plus 2 is 9. Okay? And now for this one, we use the Lars method again. So LA, right? And then RS, so R and subtract. So I'm moving to the right. That means I'm going to subtract. And how many times did I move to the right? 1, 2, 3. All right, so I moved 3 times to the right. The first number we had as a baseline is -3. If we add 3 plus -3, we get -6, which is right here. So this Lars method will help you with the scientific notation here. So basically what we're learning here is scientific notation. So if I want to convert this to scientific notation, let's practice together. So Lars, right? L-A-R-S. So right for subtraction, subtract, and then left for add. So where are we going to move this decimal? It's all decimals start here, right? And I want to do 1, 2. You always leave one place. I think it's the 10th place. So you go 1, 2, 3. Okay, I moved this 3 to the left. I also moved this 2 to the left. Oh my goodness, we have no examples of the right. Whoops. But you guys just saw the example for right for subtract, so it's okay. So then we have 6.00 if we move the decimal here. And then this one, we moved it 3.40. Right, so we moved our decimals. And now, what does that do to the exponent? So our original one looks like this. 3 times 10 to the 0 times 10 to the 0. So remember that 10 to the 0 is equal to 1. So basically, I'm just writing 6 times 1. It doesn't change the number at all. But now I moved it to the left. So technically it can't be times to the 0. It has to be something else. So it's 2 to the left. So we have to add 2. So you add 2 here. Oops, why is it there? Okay, add 2. And this one was add 3. So now we should get equals 3.240 times 10 to the 3. And that should give me the right answer that represents this. So if you do the math, that'll give you 3,240, which is exactly what we started with there. And then this would be 6.00 times 10 to the 2. Remember that you need to keep the zeros here because they're significant figures. And that's the whole thing about significant figures is this. So that's why we talk about significant figures in the handout here. See where it says significant figures down here. So significant figures, you have to include all non-zero digits, which we did when we converted it. So here are all the non-zero digits included after the 10th place here. But you also need to include 0 digits even. Yeah, because let's go here. Any trailing zeros in a number with a decimal point. So you also have to leave those in, because let's say I didn't leave them in. Then I would have, let's say 6.0. I forgot to leave in one of the zeros. And I still had 10 to the 2. That would give me the wrong number, right? So that would give me 1, 2. That would give me, oops. Where are we at? 1, 2. That would give me 600 here. Okay, you're like, oh, well, we already had that, 600. Well, kind of. So technically you could do it, but what I'm saying is that just you could just leave it and it'll be more like accurate, I guess. But it's up to you how you end up getting it the fastest and most accurate way for you. Estimation. So multiplication, if one number is rounded up, the other should be rounded down in proportion. And division, if one number is rounded up, the other should be rounded up in proportion. So rounding, you should review your ability for rounding if you don't know how to round numbers to a number that's doable for you to calculate, because on the test you will not have calculators. Okay, so now we can learn off of the sheet here. So we're learning about how do we add exponents. So as you can see, if you're multiplying two scientific notations numbers, you have to add the exponents here. So 3 plus 2 is 5, and that's how you get the 5 as the exponent there. If you're dividing two of the scientific notations, which you'll see a lot in the formulas as well, when you do physics problems, like -2 divided by this 3 here, you need to subtract these exponents, -2 and 3. And -2 minus 3 is -5. -2 minus 3 is equal to -5. Right, so you would subtract the exponents. Now, this would follow exponent laws. If you don't know already, that's okay. It's good review as well. And then if you're multiplying them like this, it's outside the bracket. You do 3 times -2 would give you -6. So if you ever see a situation where you have to multiply them like that, that's how you would do it. And now, if you ever see a square root of your scientific figure, what do you do with that exponent? So we know that for this one, we have to solve the square root of 9. Square root of 9 is 3, because 3 times 3 is equal to 9. So if I did the square root of 9, I get 3, right? So 3 is there. So I do the math as I normally would. And same thing over here, right? So 2 to the power of 3 is 8. That's how they got 8 there. And same thing for the first number here. So don't forget about that like base number as well to do it, to calculate those. Okay, and then for, right, square root, you would divide the exponent by 2 if it's that case where you have a square root. So 8 divided by 2 gives you 4. So that's the exponent that you get for that one. So those that is basically scientific notation. So it's very, very important to do scientific notation because that's a lot of the questions and answers will ask about a lot about, not specifically about scientific notation, but you'll have to use it. And then now we can go into exponents, log, and ln. So this is ln, log, and exponents. So we're going to learn these tools and shortcuts for estimating square roots and logarithms. Usually we just call them logs. So by the end of this, you should be able to look at a square root and be like, yeah, that should be close to about, I don't know, 13, 12, 10, something like that. You need to be able to do it, again, with no calculator. No calculator. For now, when you do hard practice questions, you might want to use a calculator, but on the test, you won't have one, right? So how do you estimate a square root? So what even is a square root, right? We can start there. Yeah, it doesn't even tell you that, right? But I'll go over it because I'm going to be nice today. So what even is a square root? A square root is, before you do anything, let's go into the square root of 25, right? The square root of 25 is basically asking yourself what number multiplied by itself will give me 25. So if I multiply 5 times 5, that will give me 25. But if I multiply 4 times 4, that would give me 16. This cannot be the square root of 25. This can be the square root of 25. 5. So that means 5 is the square root of 25. So square root of 25 is equal to 5. That's what you're asking yourself. What multiplied by itself will give me that number in the square root? And that's how I get the answer. Whoops, how do I delete this stuff? I just deleted like, okay, I don't know what I'm doing here. Delete, there we go. Okay. So that's the basics of square root. Most of the time, the number under the square root sign isn't a clean number like 25 actually. So that's why you will learn to estimate square roots, as we see in the sheet. The mile down sheet is about estimating square roots. So let's go ahead and learn about how we can go about that. So we obviously can have perfect squares that can occur. So we're going to go over the common squares before we go into the harder ones. So if this will load. Yeah, so the common squares are these ones here. Right, so 1 times 1 is 1, 2 times 2 is 4. So if I did the square root of 4, the answer is 2, right? And so on and so forth. If I did the square root of 49, what's the answer? Whoops. Square root of 49, what's the answer? It's equal to 7. right? Because 7 times 7 is 49. So you need to memorize your common squares. If you don't know these yet, then it's good to know your multiplication tables first. Multiplication tables, your times tables, remember those? Yeah, and then you can go on to memorize your common squares, which are all of these here. And they did it up till 20, right? So that means you might want to know your multiplication tables up to probably, not necessarily 20, but it would help. But here we have a rule sheet of up to 20. The more you know, the merrier and the better. And so when you want to estimate these squares, what you're going to do is, this is a trick. So if you got 180, square root of 180, there is no 180 here. The closest is around about in between 13 and 14, right? So step 1 is actually that step I just did, which is memorize these. And when you see a square root of 180, you're able to say to yourself, well, it could be between 13 and it could be between 14, right? So because 180 is closer to about 14 and 13, actually, it's pretty close to both of them. 180 has to be somewhere in between, right? So what you could do is break the number into perfect square factors. So 180, as I said, is not a perfect square, but some parts of it will be. So if you break 180 down, like into 4, 180 can equal to 4 times 9 times 5, right? And you notice that 4 and 9 are both perfect squares, right? So you can have square root of 4 is 2, square root of 9 is 3, and then square root of 5 is not very perfect. Okay, so square root of 9 is not really perfect, right? Now what do you do? Well, that's fine. What you can do now is realize that, you know, you can have 6 times 5. So you're just simplifying this now. 6 to the root of 5, right? So if you do 3 times 2, you get 6. 6 times the root of 5 is this notation here. So now what you're going to do is you're going to estimate the leftover square root. So you just need to know roughly what root of 5 is at that point. So you made your life easier rather than memorizing all the way up to here. We've simplified it so that you can know, okay, the root of 5 is about 25. Or sorry, not the root of the square. It's here. Sorry, the root of 5 is about somewhere lower, like 2 times 2, almost there, right? So you can kind of guesstimate. A good estimate would be 2.2. So root 5 is about 2.2. So you can estimate that. And so when you multiply it back together, you get, as it writes here, the square root of 5 is about 2.2. So 6 times 2.2 is equal to about 13.2. And we know that this approximation should be correct because we already deciphered the first time that the answer should be somewhere in between 13 and 14. So this is how you can kind of estimate your square roots. And knowing your multiplication tables will help a lot, then memorizing your common squares, and then doing practice questions on those. Now we can go into logarithms and ln. Ln I had to learn as well, so don't be don't be scared of numbers. So what is logarithm? So logarithm looks very intimidating when you first look at it, but log is basically the reverse of exponents, right? So if you learn exponent law, I don't know why exponent law is not on here. I think the textbook I had before went over exponent laws as well. So if you have the chance also for math review, go over exponent laws before learning logarithm and then come back here. How do you learn exponent laws? Well, you can just go onto Google and type in exponent laws. Exponent laws. Yeah, so you can go into Google and type in exponent laws, and there's lots of exponent laws for you to know. I already showed you one in the video where anything to the power of 0 is equal to 1. 5 to the power of 0 is equal to 1. Okay, sorry. I'm getting sidetracked now. So yeah, go review exponent laws before you do log if you're completely beginner, right? Okay, so for log, remember how square root undoes squaring, right? A log is something similar, but for exponents, and it's not just like for squaring. So here's a question that a log will answer is, what power do I have to raise this base to in order to get this number, right? So say I ask you 10 to the power of what? Let me see. Oh, this is not the whiteboard. Whoops. Let me go to the whiteboard. Let's do it. No, where's my spaces? Let's do it here. So 10 to the power of what will give me 100? So what will A have to equal to give me 100? What would that exponent need to be? All right. 10 to the power 2 will give me 100 because, your multiplication, 10 times 10 is 100. So I need 2 of these 10. So 10 to the power 2 will give me 100, right? So the question, 10 to the power what gives me 100, is exactly what the expression log 100 asks you. And so the answer is 2. Right, so that's exactly what log is asking you. It's the reverse exponents. How can I find the exponent? Finding the exponent, right? So that is the basics of log. So the formal definition and the general rule is on the screen here. See if we can get it. So we have log A is equal to log B. let me see what, they didn't write much here. Yeah, so log A is equal to log B, and then 10 to the power of B is equal to A. Sorry, I'm blocking the text here. So log A is equal to B, and 10 to the power of B is A. So this is just exactly what I just went over, by the way. So when you see log by itself with no small number written after it, that means the base is 10. So if there's no small numbers written after it, the base is 10. So you just assume that's 10. So see, these would be the base, right? Most of the time it is just 10. Yeah. So we can do some quick examples again. So log 1000 is what? Pause the video and try to do log 1000 if you're new. If you're not and you think you're like amazing, that's fine, just skip it. So log 1000 would be 3 because 10 to the 3 will give you 1000. Okay, so now you might be wondering what's ln, because we can go over ln now. Ln is ln. So if you ever see ln, which is right here, this is ln, the basic definition of ln. And so let's go into it, right? So ln, I'm going to get a new part of the board. I'm running out of whiteboard. So ln, A equals B. And we saw that EB is equal to A, right? So E, you can think of it just as a specific number. That's just like a constant almost. E is equal to 2.7 as it says on the review sheet. And so E is just a specific number, like pi is a specific number, right? 3.14. Okay, anyway, that's pi. That's not in this topic right now. Now, sometimes instead of log, you see ln. And those are in the physics formulas once you start to do a review. And it works exactly the same way as log, except instead of base 10, it uses a special number called E. So we're not using base 10. E is just a specific number, right? And E is approximately 2.7, and you don't need to know where E comes from right now for, the sake of the test. You just need to know to use it, plug it in. So ln A equals B. What does that mean? And it means the exact same relationship as log A is equal to B. It's the exact same thing, just with E as the base instead of 10. So remember, we said log 10A equals B. That's technically what it is, but we didn't write the base 10 there, right? What did we write instead? We wrote log E. It's technically E, right? Is A is equal to B. That's technically what it is for ln. So if we go back to the part that I wanted to go over, ln A basically means log E. So you're using this base 2.7 instead. A equals B. Okay, so I think I went over that, reiterated that a little bit too much. Now, the sign of log, is it positive, negative, or zero? So now we know what log means. Now we need to calculate a few special results you should like kind of recognize instantly. So these are kind of like, you can think of them as log rules, I guess. So log A1 is always equal to 0. They're kind of like log rules, what we're learning. So it's important to know your log rules, just as it is important to know your exponent rules. And then log A is equal to 1. So the log of the base itself is always 1 because A to the power of what gives. So when you ask yourself like A to the power of what gives me A, well, A to the power of 1 gives me A. So the answer will always be, but it will always be A. Okay. And then whether you want to figure out if the log is going to be positive or negative, like the answer will be positive or negative, right? Based on figuring out like if the number you're taking the log of is bigger than 1, right? If it's bigger than 1, greater than 1, if this number is greater than 1, then it should be positive. If this number is less than 1, then it should be negative log answer as an answer. So before you calculate a single digit, you need to glance at the number inside of here, right? And then which would be A or whatever it is inside of here, number. Then look at the number and ask yourself, is it greater than 1 or less than 1? If it's less than 1, then the answer should be negative. If it's positive, then it should be. If it's greater than 1, then it should be positive. Okay, and then the rest are log rules. Just like exponent rules, you can search them up like log rules. Right, so there's these log rules here that you can learn. There's basics of logarithm here, video on that too. And so I'll run over the basics that if you do log A times B, so you had a number here times this one, you could just end up adding them, the logs of both of them. If you have log A over B, then you can end up subtracting them, so log A minus log B. If you have log A to the power of B, you could have B times log A, which is interesting. If you have log 1 over A, you can do negative log A. So if you have the reciprocal of the A, you can do negative log A. Okay, and so doing practice questions will help with that. Estimating log. Now this is important because log shows up in things like calculating pH and POH and stuff like that. And when you learn about, calculating all of that in general chemistry, you also need to know how to estimate log. So the technique that you can use on the exam is exactly this right here. That's highlighted already for you. So these are fast ways to do log, and you should learn them because on the test you will not have a calculator. I've said that a million times already, but yeah, you will have a calculator. So basically, let's say I had a number that said log 2 times 10 to the power of 5. How would I calculate this, right? So how would I turn this to a normal looking number and find the answer? Well, then I can use this. So b plus 0.8. So b is the exponent, so I'll do 5. I'm doing it according to my example here. So log 2 times 10 to the power of 5 I'm now using this mental shortcut to find the answer. So 5 plus 0.8. So plus 0. Where's the a? Log a is 2. So my answer should be around 5.2. So log, sorry, I don't have a lot of space, so I'm writing down here. Log 2 times 10 to the 5 should give me about 5.2. So that's the mental shortcut to remember. You just need to remember this, right, to use it. All right, so that's estimating log. This is another thing. Log a times 10 to b is equal to log a plus log 10 to b. And then from there, you can add them up together. Log a plus b, right? So do practice questions for estimating log, and you should be good. Now, last but not least is also trigonometry, which is all of this down here. All this is really important because when you do like inclined planes and stuff like that, and you're like, there's like questions about, oh, there's a box on an inclined plane and you have to solve different stuff. Yeah, you're gonna need to know your trigonometry for things like that. Okay, so what you can do is you can firstly, if for the people that don't know what trig ratios are, because I want to make this accessible for a lot of people, we're talking about right angle triangles, right? So right angle triangle looks like this basically, with 90 degrees on the corner here, 90 degrees, right? So I'm hoping everyone passed that part of math in school. And so the trigonometry starts with that basic shape, the right angle triangle. And so now basically the math we're learning for trigonometry is basically nice labels and angles for understanding calculations later on to like then do calculations for these right angle triangles and for problems that concern it. So, right, if you pick an angle in the triangle other than 90 degrees, we're going to call it theta. Right, so that's why you see theta in here. Well, that's not the right symbol. Theta looks like this. This is a null symbol. I don't know why they put that symbol there. It's kind of wrong. The right symbol is here in this chart here. So this is theta. So every other angle is using this Greek symbol theta, and it's just a placeholder name for the angle we're looking at. You can just use x technically, right? Or y or z or whatever variable. And then we have the sides of the triangle. So you have your hypotenuse, and then you have your opposite. So let's say this was, let's say this was your area, angle of interest. It would be the side opposite. So this would be your opposite. And then this would be your adjacent, whatever's left over, whatever's beside adjacent. And we already know one of them is hypotenuse. So you have 3 sides of the right angle triangle, and we have names for them. So we have the names hypotenuse, opposite, and adjacent. Okay, so that's how you kind of label the right angle triangle. So then we have these SOHCAHTOA that will help you memorize that. So SOHCAHTOA stands for, again, what we just reviewed, sine theta, whoa, what just happened there? Sine theta is equal to opposite over hypotenuse. Okay, opposite over hypotenuse. Cos theta is equal to the adjacent over hypotenuse. Okay, tan theta is equal to opposite over adjacent, or sine theta over cos theta. Okay? So then these are important to remember, and SOHCAHTOA, this is like a mnemonic basically to help you memorize it, these formulas. So what else did I want to say? Yeah, tangent does have 2 of those, right? So now this graph chart is also important to remember. So the common values of special triangles. So these are common values of special triangles that would occur. So think of it this way. You can have a triangle where theta is equal to 0, and that would mean cos theta is 1, sine theta is 0, and tan theta is 0. So basically, if I sub in cos 0, that's equal to 0. So cos 0 is equal to 1. Sorry, it says 1. Follow the graph. Don't follow everything I say. Sine theta is equal to sine theta 0. Sine theta, where theta is equal to 0, gives you 0. And I'm just following this. This is just memory based. So you just have to memorize what would happen to the triangle when theta is equal to 0, when it's equal to 30, 45, 60, 90, and 180. Because those are all special triangles that you need to drill in. And so, yeah. And so working through the problems, they might give you like cos theta, right, is equal to adjacent over hypotenuse, right? They may give you the angle, right, which could be 30. Let's say it's 30 degrees. Okay, then you would then go use this that's in your brain. I hope you can memorize this. It'll be in your brain. And then you're like, oh yeah, cos 30 is this root 3 over 2, right? So then you'll remember, oh, cos 30 is equal to root 3 over 2. And then let's say the question's asking you, oh, then what is the hypotenuse? Well, the hypotenuse here is 2, right? Because this denominator is like stands for the hypotenuse. Yeah. So they're going to give you questions that you might have to answer stuff with. And And now there's also this unit circle. I never really go over the unit circle, but we will go over the unit circle. Using the common values in the table, plus one rule about signs, we can fill in every labeled point in the unit circle all the way around without memorizing a single new number. So the first quarter is just the table that we have. So this table is on here, this unit circle. I think it's on this side, right? This is where the table is, I believe. Let me see again. Yeah. Oh yeah, and these are the triangles here. A 45-degree triangle with another 45-degree and a 90-degree triangle. And this is special because x and x, so the adjacent and opposite sides here are equal to x. And then the hypotenuse is 2x. So the opposite and the adjacent are basically the same number. Whereas when you have 30 degrees and 60 degrees, the opposite to 60, let's say, is going to be root x. The hypotenuse is always 2x, so it's really large. And then the adjacent area is just x. So you can see here that the hypotenuse is pretty large. And this one. Hypotenuse is always pretty large. Okay, so for the unit circle, yeah. So the first quarter of our table, that starts from 0 to 90 degrees. And just make sure that was right. 0 to 90 degrees. So here's 90 degrees. Here's 0, which is going to be our table common values here. And then, so that's quadrant 1. Right? And so, yeah, it's the same thing. Reference angles, for every other angle around the circle, we can use something called a reference angle, and that's the acute angle between the line and the nearest x-axis. So it's always one of our familiar angles, which would be like 30 degrees, 45 degrees, 60 degrees. So if I ever had 150 degrees, right, it's not one of our angles here, right, like 150, but it's only 30 degrees short of being 180 degrees. So it's very close to being 180 degrees, which we are familiar with. So that means it's going to be a reference angle. Let me see if I can find it. Here, 150 degrees right here. That means it's going to be a reference angle. Its reference angle is 30 degrees. Its reference angle is 30 degrees. That means the coordinates at 150 degrees use the exact same numbers as 30 degrees. See? They use the exact same numbers. All right. Just with different signs. So you see this is negative root 3 over 2, and this is just positive everything here. Okay, so yeah, for quadrant 1, which is 0 to 90 degrees, it's all labeled here for you, so I'll just delete the annotations so it's easier to see. 0 to 90 degrees says 0 here, 90 degrees. All of this is always x positive, y positive, like how you would expect on a graph, right? So this is all positive, y positive, because y is going up and x is going up. And then this is quadrant 1. In quadrant 2, which is 90 to 180, so where's 90? It says 90 here to 180 here. So this quadrant is going negative for x, right, and positive for y still, right? So that's why you get the different sign that you get here, but the numbers are the same, right? And now you can go over to quadrant 3 and then quadrant 4. So quadrant 3 is 180 to 270. All of this is quadrant 3 going on here. This is quadrant 3. And so quadrant 3, oh my goodness, I have too many annotations. Quadrant 3 is where you get this y is finally negative because it's going down, right? And the x-axis is also negative. So both these numbers you'll notice are negative. They're all negative here, right? And then if you go over this quadrant, right? So this quadrant has x-axis going positive, and it has y-axis going negative. So only x is positive and y is negative. Positive. So x is positive, y is negative. So cos is always positive and sine is always negative, in other words. Remember quadrant 3, right? You have both x and y are negative, so cos and sine are going to be both negative. Quadrant 2, right here, x is negative, it's going to the negative side, and y is positive, right? So that means cos is negative and sine is positive. And then for this, well, everything's positive, so happy. Quadrant 1 is just like the happiest one, I guess. So that's the unit circle. And so in the unit circle, the reason why I was saying cos and sine and y, so remember y is equal to cos theta, and x is equal to cos theta and y is equal to sine theta. And so tan is going to be equal to y over x, which is sine theta over cos theta. That's kind of how it relates to the theta formula over here. Tan over here, it relates. And so these are important to help you read the unit circle, because if you have positive x, remember I was talking about positive and negative x and y. So if you have positive x, you get positive cos theta. If you have negative x, then you get negative cos theta. So again, let's say you were in the quadrant 2 and your x was going to be negative because it's going onto this side, left, on the x-axis, then you would have a negative cos, right? So these are important to understand, help understand the unit circle, right? Okay, so that's the math review. Now I can actually move on to the actual physics stuff. And we'll move on to chapter 1 of physics. So I'll put a check mark on this, check mark. Yay. All right. So we're going over vectors and scalars now, and that's the first chapter on chapter 1 on the physics textbook. So vectors and scalars are basically, a scalar is a quantity. So you can think of things can have a direction, right? Like if I measured 50 meters, that doesn't have a direction, but if I said 50 meters to the right, that's a vector because it's direction. It has a direction to it. This quantity then has a direction to it. If I say it's scalar, then it means that the quantity that I'm measuring doesn't have a direction. It is what it is. Doesn't have direction. So when I say scalar, a unit that can be scalar is known as, also can be an example of speed. Speed is scalar. It doesn't need a direction to be meaningful, right? Whereas if I tell you a car is going 60 miles per hour heading north, all of a sudden, it's heading north, so this way, all of a sudden it's a vector because it has that direction to it. So that is basically what a vector is and a scalar is. So as it reads here, vectors are physical quantities that have both magnitude and direction. So your magnitude would be the number here, like 50, 25, that's your magnitude, or it could be like negative 25 even. Things like that, and then your direction as well. So examples include displacement, velocity, acceleration, and force. Those are vectors. Scalars are quantities without direction. Scalars may be, let's go on the review sheet so it's easier to see. So scalars may be magnitude of vectors like speed, or maybe dimensionless like coefficients of friction. Vector addition is a tip-tail. You can use a tip-tail method, or you can break the vector into its component parts and use Pythagorean theorem. So how do we now add vectors is the question. So we have some space here to write adding vectors. So because vectors have a direction, you can't just add their numbers together like regular, like 2 plus 3 plus 5 equals, I don't know, you get 10 meters north or something like that. No, that's why we have a tip to tail method, as it says. So tip to tail is basically where you go, you draw, okay, let's say you have one vector going this way. All right, and then you draw a second vector starting exactly where, this is where trigonometry comes into play, by the way. So now you draw your second vector starting exactly where the first one is. So this is the tip of vector 1. Vector 1. Now I'm going to go draw another vector. This is going to be vector 2. Okay, so vector 2 has been drawn. So the second vector is starting where the tip of the first one is, right? So I said that was the tip. Now the combined result of these two, so the tail of vector 2 with this starting of vector 1 over here, the combined result of them is called the R resultant. Sorry, not R, but resultant. R stands for resultant. So it's basically from the very start of the first vector to the very end of the other. Right, so this is the start of vector 1, and this is the end of vector 2. This point here and this point there. So that gives you your resultant. All right, so then we can trace this back to Pythagorean theorem, which has to do with our, okay, that doesn't look like a right angle triangle, which kind of has to do with our right angle triangles in our trigonometry that we reviewed. So that's our first method of finding the resultant to add vectors up. The second method, it says you can break them into component parts using Pythagorean theorem. So for Pythagorean's theorem, if you remember, is a squared plus b squared equals c squared. And so you can break the vector into its horizontal, which is x. X is always horizontal, and to y component, which is vertical. Right? So if you've ever seen a graph, you've always seen x going left or right, and then y going up or down, right? Y-axis, x-axis. Okay, so if you add all the x together, right, x components of x together, and then you add all the y together but separately, and then you use Pythagorean theorem, you can find the magnitude of the result. So that's how you would use then Pythagorean theorem for that. What else does it say you can do? We're going to go on to vector subtraction. So subtracting vectors uses the same tip-tail method. If we go back, so subtracting vectors, you just change the direction of the subtracted vector and then use tip to tail addition. So same tip to tail method, tip to tail, but with an extra step. So you flip direction of the vector you're subtracting. So you point it in the opposite way. And then you add it to tip to tail like normal. So for multiplying vectors by scalar, it changes the magnitude and may reverse the direction. So when you multiply vectors by a plane number, which is basically a scalar number, this changes the vector's magnitude. It can make it longer or shorter, basically. So instead of, I don't know, 50 meters, you get 100 or something. That makes it longer. And if you multiply by a negative number, it flips the direction completely around. Yeah, vector multiplication. But you have to understand that vector multiplication can lead to two different types of products as well. You can have a dot product or a cross product. So the dot product takes two vectors and produces a plane number. It produces a scalar result. So dot product produces a scalar. This would be scalar. A cross product produces a new vector, results in a new vector. So the direction of the vector can be found using the right-hand rule. So this is a rule that you would use it with your fingers in real life. So your dot product, again, let's say the magnitude of vector A times the magnitude of vector B times cosine of the angle between them, which is your dot product. Let's say the result tells you how much the two vectors point in the same direction as each other. So if they point the exact same way, where theta is 0 degrees and cos is 0, cos 0 is equal to 1, so you just get a plain product of their magnitudes. If they're perpendicular, so 90 degrees, where theta is 90 degrees, cos 90 is equal to 0, so the dot product is going to be 0. So the cross product then takes two vectors and products and produces a brand new vector, right? So that gives you, for example, a magnitude of the new vector. Okay, so it's a new vector, but a vector also needs direction, and for the cross product, that direction is always perpendicular to both the original vectors. And to figure out which way it points, you'll use this right hand rule with your fingers. So basically, the right hand rule is where you point your fingers in the direction of the first vector. So if the first vector was pointing north, I would point one of my fingers upward, right? And then you would then curl them towards the second vector, and your thumb points in that direction as a result. And so you use your right hand to figure out where would this go. I'm going to show a picture instead of the right hand rule because it's hard to visualize the right hand rule for cross product. So search it up, watch a YouTube video on it, but this will also show you. So you would point your direction of A wherever it is. There's also like modifications of the right hand rule. Some people do it like this way or something like that, but you can also use your three fingers. So let's say A was facing, to the left, vector would be facing toward you, and A and B would be facing upwards. And so that's how you can figure out the direction in 3D space with your right hand rule with your fingers, or your hand, whichever method you're using, but the main method is usually with your fingers with the right hand rule. Okay, and now we can go into, what should we do next? Displacement and velocity. All right, so we went over that vectors and scalars, like you can have 50 meters, that is scalar, or you can have 50 meters over an hour in the direction that is north, and that's a vector. You have some direction and magnitude. And so displacement and velocity is like what I was talking about here, is talking about time. So displacement is the vector representation of a change in a position, path independent. So displacement is basically the vector representation of your change in position. So it's literally just where did you end up relative to where you started. So if I was a track athlete and I ran in a circle, right? Where's my position to where I started? The displacement, what is my displacement? Displacement is actually 0, even though I ran through the entire track. You're thinking, oh, didn't you run a distance of like 400 meters? Track is 400 meters, right? Isn't this 400 meters? Wouldn't I be displaced by 400 meters? No, because I went back to the place I started to. So displacement is equal to 0 in this case. Distance is a scalar version, and it does care about the path. So remember that displacement is path independent. It doesn't care about the path you took. Even if I ran 400 meters around the track, it's a 400 meter track. It doesn't care about the path I took. It cares about where I ended up, which is right back at where I was, which means my displacement is 0. If I landed, 10 meters ahead, then then where I was, like the starting point, then that would be plus 10 meters, right? In a clockwise direction. But for distance, the difference is that it's scalar and will reflect the path I traveled. So that would be 400 meters. I ran a distance of 400 meters. So that's a difference between distance and displacement to get down. Then we have the speed at which we accomplish those displacement or distances. So velocity is a vector representation of how fast your displacement is. How fast is your displacement? Average velocity is total displacement over time. That's a formula to remember. And your average speed is scalar. So it's the total distance traveled over time, not displacement, distance. And then you have instantaneous velocity and speed. So everything so far has been an average over a stretch of some amount of time. But what about your velocity at an exact point? That's when you talk about instantaneous velocity and instantaneous speed. So instantaneous velocity is what you get when you shrink that time interval down smaller and smaller until you approaches 0. So it's your displacement over time, but measured over an interval so tiny, it's basically instant. That's why I call it instantaneous velocity. This is the exact reading you'd see on a speedometer, but as a vector with direction included. And then for instantaneous speed, right, it's just the magnitude of that instantaneous velocity vector, the number on your speedometer, direction without any direction, right, because it's a scalar. Speed is scalar, remember that too. Okay, so we went over vectors and scalars, which is great. Now we can go into forces and acceleration. So what is a force? A force is any push or pull that has the potential to result in an acceleration, right? So a force is simple. It's a push or a pull. And anytime something pushes or pulls on an object, that's a force that acts on it. And forces are what can change an object's motion. So gravity is a force, right? So the apple falls down the tree, right? Any two objects with the mass pull on each other just by existing. And that's gravity. You don't feel the moon pulling on your coffee cup because the pull is incredibly tiny, but it's technically there. The pull becomes noticeable when at least one of the objects, like an entire planet, like that is enormous. That's when you can feel the pull. So the attractive force between two objects as a result of their masses. That's what gravity is. Friction is a force that will oppose motion as a function of electrostatic interactions. So okay, let me try to explain this. So when you have two surfaces touch each other, you have tiny electrical interactions, right? Electrical interactions between their surfaces, and they're resisting each other. That resistance, the resistance is friction. So there are two different types of friction. There's static friction and there's kinetic. Static and kinetic. And so static friction is where you have an object that is sitting still, static, a stationary object. It's sitting still, and so it's the friction resisting the start of a motion. Resists any start to motion. And kinetic friction applies to an object that's already sliding, so kinetic. If you learn about kinetic energy, you can kind of relate it to that, but if you didn't, that's fine. Kinetic energy applies to an object that's already moving. It's the friction resisting motion to something that's already, in motion. So then we have the formula, this force is equal to U times N. So the friction force, this mu, this is called, I don't know why it says U, it's actually like this. This is the coefficient, that's how you write it, and that's how you see it in practice question. It looks like that. It looks like a U, but it has a longer tail at this left side here. Anyway, that is called the Greek letter mu, and it represents the coefficient of friction. It's a scalar quantity, and it's multiplied N. N is known as normal force times N. N is known as your normal force, and that is the force pressing the two surfaces together perpendicular to the surface. So when you do physics, always try to draw diagrams, and lots of diagrams. So if you have this inclined plane here, and you have a box here, there might be kinetic friction, with the box is moving down this way, right? There might be kinetic friction, but we're talking about normal force. So normal force, again, is the force pressing the two surfaces together perpendicular to the surface. So here's the surface. Parallel to the surface would be this way, anything going down in this direction. But perpendicular looks like this, right? So opposite. So that would be, here's the surface, opposite would be this. So the normal force is in this direction, down, perpendicular to the surface. This is the surface. Okay, so that's normal force. And so you get the coefficient times normal force is equal to friction. All right, so for mass and weight, they're different things. Now, I didn't really come in with the strongest physics background, but learning all the terminology helps, and then doing the practice questions later on. So mass measures how much stuff an object is made of, and so how strongly does it resist being accelerated. So for example, a bowling ball has more mass than a tennis ball. Right, so it's made up of a lot of stuff. So it's just much harder to speed up or slow down. It's much harder to move a bowling ball. If you ever felt a bowling ball, it feels heavy, right? So mass is a measure of inertia of an object. It's the amount of the material, right? And so weight, on the other hand, is a force. It's a force, specifically, it's how hard gravity is pulling on your mass. So this is why your weight would change on the moon, right? So you might be a different weight on the moon, but your mass is the actual amount of material you're made of. So it stays exactly the same whether you're on the moon or not on the moon. Weight is like, it calculates too about the gravity, right? And so mass is a property of you, but weight is a force of gravity that applies on you. So this is why it says by given mass due to the gravitational attraction to Earth. So this has to do gravity on Earth. Has to do with gravity on Earth as well. Okay, so acceleration. What is acceleration? So just like velocity that we described over here, that's why I went through velocity first. Acceleration is basically how position changes over time, but acceleration instead describes how velocity will change over time. So that's why I went over velocity. How does velocity change over time? So let me think of an example. So velocity is a vector. Remember that. Acceleration would then be a vector too. So speeding something up, slowing something down, or even just changing direction while moving at a constant speed will all count as acceleration. And so torque, so far we've discussed things that kind of move things in a straight line. So you're either going this way, or up or down. But torque, if you look at a picture, actually, it would help people see a picture of torque. So torque, see this torque has this formula here. Torque is equal to R times F, absolute values, times sine theta. So when I move something, right, there's a force acting on that. And so every force we discussed so far, again, is a straight line, but torque is different because it's a force that causes something to rotate, like a wrench or pushing a door, right? So torque uses this tau symbol here. This is called tau symbol. Tau, it's not really important that you know it's tau, but I'm just showing you. It's the distance from the pivot point, that would be R. So R is the distance. So from the pivot point would be your radius, And then what else do we need to know? Sine theta, where is the angle between your push and your lever arm. So here's R, and then sine theta, there's theta here. That's the angle. Okay, what else do you need to know? Yeah, so torque also has a direction, but instead of a full 3D direction, we just track it whether things are spinning counterclockwise, which we would consider positive. As you can see here, anything counterclockwise, so clockwise is in this direction, right? But if you're moving from 12 o'clock this way to this way, it's counterclockwise. If you're moving this way, it's clockwise, right? So depending how it's moving, right, that its direction is kind of shown by positive and negative. If you have positive torque, then it's moving counterclockwise. If you have negative torque number here, then it's moving clockwise. Positive, counterclockwise, negative, clockwise, sorry. And then what else do we need to know? Newton's laws, right? So Newton's law has first, second, and third law. The first law is often called the law of inertia. Law of inertia. It's also called that. So if nothing is pushing or pulling on an object, or if all the pushes and pulls are perfectly canceled out, then the object will simply stay at doing whatever it's doing. So a ball that's staying still, for example, it's not doing anything, won't do anything if, nothing is going to act on it. For example, hockey puck sliding across a frictionless ice keeps sliding at the same speed forever until something will eventually act on it. And that's the first law for Newton. F net means net force, mass times acceleration. So the combined result of every force on an object at once added together as vectors. So the F net is the combined forces. Okay, what else do you have to know? The second law. Okay, let's move on to the second law. So it's a famous equation, and it states that the net force is equal to mass times acceleration as well, but this time it's not equal to 0. So this one was equal to 0. This one is just mass times acceleration. So if you push harder and apply more force, right, you get more acceleration. If the object, so F will go, if F goes up, then A will go up. And that's how you kind of tell about proportionalities when you get a formula like this. If it's equal, F and equal to A, then F is proportional to A in that if I increase F, A will go up. If I decrease force, then A will go down. Proportionality and stuff from formulas is important on the MCAT to see how different things affect each other. Mass, if the object is heavier and you have more mass, the same push produces less acceleration. And this single equation is behind every force problem that you're going to be solving, so it's important. The third law of Newton's law is FAB is equal to negative FAB. So you have a negative FBA, whatever. So it basically means equal and opposite reaction. So if you push on a wall, the wall will push back with an equal and opposite direction. So here's my wall, and I'm going to push on the wall, right? The wall is going to push back equal and opposite. That's basically what it's saying. All right, now we can go into mechanical equilibrium. So for mechanical equilibrium, every situation is a little bit different in a way. So before you solve any force problem, you can think of these as your tools, right? So I have a set of tools that can help me solve my physics problems, right? And so a free body diagram is a tool I can use before solving a force problem. And you will draw a free body diagram, which is a simplified sketch of just the object that the practice problem is talking about, with an arrow drawn for every single force that's acting on it. So forces acting on the object. So for example, you would put in gravity that's pulling it down, a normal force that's pushing up, friction, any applied push, if there's a person pushing the box or something like that. This picture will exactly see all your F net forces, so F net, right? So that will help you with understanding what's happening in terms of the forces that are acting on the object. Translational equilibrium is another tool, and so translational just means a straight line of motion as opposed to rotation. An object is in translational equilibrium when every force acting on it cancels out perfectly, so the net force is then 0. So this connects back directly to, Newton's first law. So occurs in the absence of any net forces acting on an object, right? So an object is in translational equilibrium when every force acting on it cancels out perfectly. Okay, and then rotational equilibrium, which is this one, I kind of drew over it, which is not good. Rotational equilibrium occurs in the absence of any net torque. So similarly, an object is in rotational equilibrium when every torque acting on it cancels out. So nothing is causing it to spin up or down. And so this is when it's still, resting, right? So part of your toolbox that you have to understand is that translational equilibrium is when nothing is moving, right? So you're in your resting state now. So it's connected as well to your first law of Newton's law, where, if no force is acting on it or it cancels out, then it's 0. There's no movement happening. And then the same thing with rotational equilibrium. And so when you get these, and then when you draw your free body diagrams, they can help you answer questions better and better understand things. Last but not least is kinematics. Kinematics was hard for me to learn. Kinematic equations were hard for me to memorize. But trust me, if you do Anki, it won't help as much. But if you do your practice questions for these, it will help a ton. It will help a ton because you'll be drawing diagrams and you'll be applying in context. And physics in context physics without context, does not really matter. Physics with its context is really important. So drawing lots of diagrams can help you kind of understand the material deeper and help you memorize deeper. And then maybe use flashcards afterward to help you, but use it as a supplementary tool, not like your main tool for learning. Okay. Sorry, I just had to move my chair. Okay, so motion with constant acceleration. So we've built up our toolkit so far, and now we can finally have more difficult practice problems. And so that's where we get into kinematics. So when we want to think about doing linear motion, we will use these 4 kinematic formulas to help us solve for problems, right? So these are called kinematic equations, and they're basically what you're going to use for your toolkit to answer things. So let's translate each of these equations into normal English. So this Vf equals V0 plus A delta t. And this is your final velocity is equal to your starting velocity plus acceleration and any change over time, delta t. Okay, the next one, let's do this one. So delta x is your total displacement, and then it's equal to your starting velocity times the change in time, so delta t, plus half times acceleration, delta t squared, right? So this will give you total displacement here. Okay, and then you have this equation here, which is vf squared. So your final velocity squared is equal to your initial velocity squared plus 2 times acceleration times your displacement, your change in displacement, which you can also find with this equation. So your change in displacement can also equal the average velocity multiplied by the difference in time, or the change in time, if A is equal to 0. So what this note flags, or what it's trying to say, is that it's a special case when there's no acceleration at all. So this would be used when you have no acceleration at all, and velocity never changes. So the average velocity is just the constant velocity itself, and so this is simply speed times time formula, which you already know. You already know about that formula from here, right? So this would be this formula. Whoop, how did I draw that? This would be this formula. Okay, now we can get into linear motion. Linear motion includes free fall motion, which the velocity and acceleration are parallel and anti-parallel, so you use these equations for linear motion. And we already went over the equations. For projectile motion, it contains an x and y component, assuming negligible air resistance. The only force acting on the object is gravity, so x velocity is constant throughout. So projectiles just kind of look like this. So let's say I had literally a projectile, like a cannon, and it shot something upward, right? So this is a projectile. It has a y component going up and down. That's your y component. It has an x. That's your x. This is your y. So that's what it's talking about there. So you'll have practice questions on that. You should do them. Inclined planes are force component. They have force components. And remember, at the projectile, some things to know is that it doesn't write it on the review sheet, but there's some things you pick up, like at the peak, what is happening at the peak, right? What is happening at the peak versus what's happening here? It's in motion. At the peak, gravity is pushing down on it fully, right? It's pushing down. Gravity is pushing down as you go down here. Gravity is also pushing down here, but look, gravity's taking a big hit over there. Anyway, but as you do more practice questions, you'll get more information and expertise, I guess. So inclined planes, what do I want to say about it? I've drawn pictures of it before. There's a parallel component of a force to the ramp, which is sine theta. So sine is sliding down the slide. And then there's a perpendicular. So there's these forces. So parallel, as I said, is going to be sine theta. And then the perpendicular, where does it say perpendicular, to the ramp is cos theta. So this would be perpendicular is cos theta. Okay, is that all we have for that one? Yes. And then we have circular motion. Circular motion is best thought of as radiotangential dimensions. And the centripetal force vector points radially inward. So when you look at centripetal force of something rotating this way, centripetal force, so here's your pivot point, whatever. Your centripetal force is moving this thing inward. So I'm going to get a picture of centripetal force. Centripetal force. I don't really like this diagram. Yeah, so it's the force making it move inward here. This is good. You ever spun something and the ball is kind of like pushing inward or something? This is good. These are good diagrams too. Alright, so that's centripetal force. I'm going to put this somewhere else. We're going to be on chapter 2 soon. And so you use this formula here, Fc, so the force centripetal is equal to mass times velocity squared over the radius from the pivot point. So that's centripetal force for circular motion. And so do lots of practice questions specifically focused on kinematics. But don't forget about all these other ones. So do about force first as a beginner with Newton's law and velocity and displacement, and then go on to do more kinematics and stuff in this box afterward. So I kind of went to easy to hard difficulty for everyone. Okay, next is physics 2. So I'll get back to that after a water break. I forgot I wanted to do this practice question before I went on to chapter 2. So I'm going to give an example practice question, but you're going to have to do many more than the example I'm just showing now, okay? So just because you saw me do one question doesn't mean, you know the entire chapter. But here's one practice question here. So we're talking about a 4 kg box. So a 4 kg box slides across a horizontal floor at initial speed of 6 meters per second. Right, you need to understand your SI units, by the way. I don't know, it's not on the review sheet. I don't think it even said anything about that, but you need to review SI units and what those are. So SI units give us meters per second, and those are the units that we would use, standard units to use. So review SI units if you're a complete beginner, right? So know those. Okay, anyways, and then come back here. So your 4 kg box slides across a horizontal floor. So this is the box on the horizontal floor, and it's sliding at 6 meters per second. The coefficient of, so this is coefficient of kinetic friction. So friction kinetic, I'll just write that, is equal to, between the box and the floor, is equal to 0.3. Approximately how far does the box slide before coming to rest? And gravity is equal to, gravity is always equal to 10 meters per second squared. I'm not sure if that said on the review sheet. Did it say that? Oh, that's sad. Does it say it here? Wow, there's some stuff missing here. Okay, that's sad. We don't have that on the review sheet. Well, gravity, by the way, will always be 10 meters per second squared. It's actually like a little bit less than that. I think it's like 9.8, but when you're doing the MCAT, you don't have a calculator, so you can just round it to 10 and it'll be fine. You'll be fine. So then you always draw your diagrams like I'm doing here, and then figure it out. So approximately how far does a box slide before coming to rest? So what you're gonna do is understand like this. So kinetic friction, this is what we're talking about here, is not only horizontal force that's acting on the box. Remember that Newton's second law gives us ma is equal to this. And you're like, oh, that doesn't look like Newton's second law. But look, Newton's second law is here. That's why physics can be hard for new learners. It was hard for me too. So anyway, that's what it looks like here. F net is equal to ma, right? Ma is equal to the coefficient, friction coefficient, times mass times gravity. Gravity is acceleration in this case, A. Okay, so, right. So the first step is to understand that friction is the only horizontal force that's being applied, right? Remember, this is the only horizontal force being applied, friction. And so F net is equal to, what is the total net forces acting on this object, right? That's what we're looking for, basically. So the forces total acting on this object include your coefficient times the mass of the box times gravity. So F net is equal to ma is equal to mg. So you're just multiplying to get the force acting on it. And then mass cancels out on both sides. So let me just show you this. So ma here. So you can just cancel this out. Acceleration is equal to the coefficient times gravity. And remember, always go back to what the question was asking you. So it was asking approximately how far does the box slide before it comes to rest. So in that case, right, how far does the box slide? Well, this box is sliding. A is equal to 0.3 times gravity. 10 is equal to 3 meters per second squared. So acceleration is equal to 3 meters per second squared. So now you have to apply your kinematics formula now, kinematics. And the one we're going to use is to find essentially your, like if I do v final squared is equal to v0 squared plus 2a delta x. So what we're trying to find again is our displacement, right? But what we need to do is use what we already know. So we knew that our v final is going to be 0 because eventually the box stops. So anytime an object stops, right, its velocity is equal to 0. So the final velocity of the box is 0 equal to, and the initial velocity is it's moving, right? So what was the initial velocity of the box? So anyway, delta x, we're going to rearrange this to find this displacement here because that's what the question is asking for. So delta x is equal to v0 squared over 2a. Right? And so v0 squared, remember 3 over here. 3 goes over here where acceleration is. Remember, we saw for acceleration A is equal to 3, right? So you would plug that in. So delta x is equal to v0 squared 2 times 3. Then you get 6. Now our v0 squared is 36. It's 36. And so what do we do with this one? This was given to us in the problem. So remember it said, where did it go? It says initial speed is 6, right? So then you would just plug that in and you do, where is it? 6 squared is equal to 36 over 6, which gives you 6. So your displacement should equal to 6 meters, right? Or how far the box is sliding, sorry, should equal to 6 meters. So if we go back to the question, it should be 6 meters here. All right. So that's an example of a combination of using not only Newton's law, but everything. And that's how you kind of see it on the test. You won't just see it as like discretely, how do you add vectors? You know, it's not like your typical course where they make it like kind of easier. No, they're adding up all of this, so you make sure how everything works in combination with each other. All right, so let's go on to, work and energy. And I'll try to give one practice as well for that. But let's move on. One sec. Okay, so Physics and Math 2, Chapter 2, CH2 is about work and energy. So energy, does it even say the definition of energy here? It says it here, structural proteins. Anyway, you could take this as the definition of energy, basically. So energy is a property of a system that enables to do something or make it happen, including the capacity to do work. SI units are joules. So you should know your SI units, as I said in the last chapter. So if you don't know by now, review your SI units before doing physics questions and stuff like that, just so it's less confusing. So joules is equal to kilograms times the mass squared, or sorry, it's not mass squared, it's meters squared divided by seconds squared. Sorry, my head. I know it can get confusing as well because M can sometimes look like mass and sometimes it will look like meters, but in this case it's meters for joules. So that's energy. So this is the definition of energy. And then you have kinetic energy. So kinetic energy, it's important to memorize the formula here. And the formula is kinetic energy is equal to half mv squared. You're going to use that for a lot of practice problems. And so kinetic energy is energy of something associated with objects that are moving. So any moving objects, you're going to end up using kinetic energy. Potential energy is energy stored within a system. So you can think if kinetic energy is energy of motion, potential energy is a potential energy stored within something. So it's just energy that's waiting to be released. So for example, a stretched rubber band is one example. A ball held above the ground is another example. A battery, all of these have potential energy sitting inside of them, ready to do something. The instant that a force is acted on to them, an instant that they're basically allowed to act, that is then your potential energy. Gravitational potential energy is the most common type. It's energy stored because of an object's height above a reference point. So if I had, again, if I had a ball 10 meters above the ground, this is 10 meters. The ball's we know just by living in this world that the ball's gonna drop. It has gravitational potential energy. And so the formula is mass times gravity's acceleration. Gravity, which is 10 meters per second squared, as we saw in our last practice question. And so you can calculate for gravitational potential energy. And so the elastic potential energy is energy stored. So it's still a potential energy as well. But it's energy that's stored within something that's like springy. I don't know if you've seen any springs before, but if you release on the spring, it's like energy. The formula looks a lot like this formula. For kinetic energy, elastic energy formula looks very similar, but they're not exactly the same. So it's 1/2 times the spring constant, K. They will usually give you the spring constant, or you will have to solve it by solving the other variables, times how far it's stretched or compressed, X squared. So an example you might have is a spring with a spring constant, K equals 200 newtons per meter is compressed 0.1 meters. How much is the elastic potential energy? So that's a simple question where you just plug in the variables, for example. Electrical potential energy is also potential energy, but it's electrical. So the energy between two charged particles. This is because their charges, it's under a underlying idea of gravitational potential energy too. So it's just made for electrical charges though. So electrical charges can be pulling or pushing on each other instead of like masses. So this is about electrical charges. And then chemical potential energy is potential energy stored inside the bonds that hold the molecules together. So there is energy that is holding molecules together. So when you burn fuel or digest food, for example, so if you review in biochemistry, you're breaking bonds, or even in chemistry, general chemistry, whenever you break a bond, right, you're releasing that potential energy that was locked inside of them essentially. Let's go on to conservative and non-conservative forces. So these two. So this is important to learn, kind of not separately, but together, learning conservative forces and non-conservative forces, these two. So conservative forces is one where the work when the work it does only depends where you started and where you ended up, not the path you took there. So it's path independent. That's why it says path independent there, path independent. So if you climb a mountain by climbing a steep trail upwards, or by having a long winding trail, like that's flatter, I don't know. Either way, gravity does the exact same amount of work on you overall because you gain the exact same height. So if I climb this mountain, let's say this mountain was a bit less steep. So this hill was steep, right? And this was less steep, but I traveled to, there's too many stuff going on here. I traveled to the same height. So this is the height of both the mountains is the same, right? So if I traveled the same height, conservative forces would be like, oh, it's conservative. So it would have been the exact amount of work involved to get there. And crucially, conservative forces don't like waste any mechanical energy. None of it leaks away as heat or sound. So you can think of conservative forces in that way, where it's path independent. Whereas non-conservative forces, they do care about the path. The path does matter for non-conservative forces. So for non-conservative forces, it's path dependent and cause dissipation of mechanical energy out of the system. So what does it mean for mechanical energy to go out of the system? Out of system. So energy is going out of the system essentially. And so friction is a classic example of that. So slide a book 1 meter across a rough table and friction removes some energy as heat. Slide it 5 meters, slide a book 5 meters on a rough table and the friction removes 5 times as much. So the path matters when you're doing non-conservative forces. So if you can name a force that literally makes things warm as it acts, like friction rubbing your hands together, air resistance, heating, and re-entering spacecraft or airplane, whatever, that's your signal it's non-conservative, right? Okay, so this is important to understand. Work is awesome, but work in terms of physics, the definition is the process by which energy is transferred from one system to another. And so in everyday language, work means putting in the effort, right? People say, oh, you gotta work harder or whatever, put more effort in basically. But in physics, work has a more specific meaning. It's about the actual transfer of energy. So it's talking about the actual transfer of energy from one system to another system. And that's caused by force acting through a distance. So work done is equal to force times displacement can also be equal to force times displacement times cos theta. So work equals force times displacement. Remember the dot product that we learned earlier, right? This is related. This is a dot product. So that's what it is, right? So if you push something exactly in the direction it's moving, such as theta equals 0, and so cos 0 is equal to 1. Right, so if something's moving in the exact same direction, then cos theta would be just equal to 1. But if you have something moving in a different direction than cos theta, we would have to use our trig. Remember our trig values to help solve this, right? Okay, let's go on to power. All right, so for power is the rate at which work is done or energy is transferred, and the SI units is watts. So watts is equal to joules over seconds, or in other words, time, joules over time, basically. So let's say a simple example, a machine does 500 joules of work over 10 seconds. What's its power output? It would be 500 divided by 10 is equal to 50 watts. That's a simple example for power. Work energy theorem. Work energy theorem is also important to know. This is one of the useful shortcuts in all of mechanics. So the work energy theorem says that the net work done on systems, so total work total, so work from every force acting on it combined always exactly equals how much its kinetic energy has changed. So delta K. So it's K final minus Ki. So you notice whenever in math you get delta T or delta K or delta whatever, for those who are just new to math, I'm trying to explain it out for those who, or maybe you haven't learned it in a while, but delta means like usually final minus initial value. The change in time, for example, would be the time final minus time initial. So let's say you start at a time of 0 seconds and your final was 30 seconds. So the difference in time was 30 seconds, for example. So that's delta K. So the work energy theorem, it's useful because it lets you skip a lot of complicated force and acceleration calculations and stuff, for example knowing how fast was it going before, how fast is it going now, and to how much work has happened. So this kind of you can use in the work example that I have for you guys is think of a 1,000 kg car and it's cruising at 20 meters per second when the driver slams the brakes and comes to a complete stop. How much work did the friction do on the car? Right, so let me do the example here for work. So work energy theorem, right? So let's draw the car. This is my car. It doesn't look very good. That's my car. And it's a 1,000 kg, pretty heavy car, and it's going at 20 meters per second, and the driver decides to slam the brakes. Now we're wondering how much work did the friction do on the car? So remember, Ki is equal to half 1,000. So we need our kinetic energy formula, remember? 20 squared, velocity squared. So we just plug in those numbers that we were given. And then K and then you multiply it, so that would be 200,000 joules. And then Kf is equal to 0. Why? Because the driver slammed on the brakes. So whenever you're moving, you know, and then you stop moving, right, at rest, what are you at? 0 meters per second. You're not even moving. So if the formula is half mv, sorry, I'm not writing it right. If the formula for kinetic energy is half mv squared and v is equal to 0, that means anything multiplied will just equal 0. So kinetic energy final is just equal to 0. So then you do W net, which is your work energy theorem, Kf minus Ki, which is 200,000 joules minus 0. So how much work did friction have to do to stop this car? It would have to do negative 200,000 joules to stop the car. Why is it negative? It's because the brake is going in the opposite direction. This is where your Newton's law kind of connects and builds onto equal and opposite, right? The third law of Newton's law. So that's why learning the chapters chapter by chapter is really helpful, because this Newton's law then builds on how you know it's negative, right? Because if the car is going in one direction, this direction, then you need an equal and opposite force to be able to stop it, right? And so that force would then have to be negative if this is positive, right? So that's why it's a negative number for the work done for the brakes, Okay, so that's an example for the work energy theorem. Then we can go on to mechanical advantage. And so for mechanical advantage, it is the factor by which a simple machine multiplies the input force needed to accomplish work. So mechanical advantage, you need to know it in context a little bit. So we like to use systems that help us accomplish work easier. And so if you think of some systems like pulleys, for example, they can help us. Inclined planes are another example. So like a ramp is an example that can help us and gives a mechanical advantage. So think of those simple machines, right? And so a machine can't create energy out of nowhere, but it can trade force for distance. Okay, it doesn't, okay, remember this, that I said this, that machines, the simple machines, right, they're not, the input force necessary to accomplish the work is reduced, and the distance through which the reduced input force must be applied is increased. So you have to increase the distance. The machine can't create energy out of nowhere, but what it's doing is increasing the distance so that the force is less that you need to apply, that the person would need to apply. So on an inclined plane, right, if the person wants to help push this box down, the plane is going to help them push this box down this incline, right? But now the force that the person needs to apply is going to go down less because the plane is helping them. It's a simple machine helping them. And so, but the distance would have to increase because, you know what, the machine cannot create energy out of nowhere, right? So the ideal mechanical advantage of an inclined plane, MA of an inclined plane, looks like this. So the theoretical ideal is MA is equal to length of incline over the height of the incline. And simple machines include inclined planes, wedge, wheel, axle, lever, pulleys, and screws. And so you can also measure the efficiency of the machine's work, which is MA is equal to F, so force output over force input. So let's say we have a 1 meter high ramp, right, with an ideal mechanical advantage of 5. So MA is equal to 5. Now let's say you actually use this ramp to push 100. So using this ramp, right, well, I have a lot of annotations happening here. So let's say you use a ramp, and we're doing efficiency, by the way. We're doing mechanical efficiency. So we want to know how efficient is this machine, right? So you don't have to think of it as a machine, but it's a simple machine. So you have this ramp, and it's 5 meters this way, 5, and it's 1 meter this way. Let's just say that. With an ideal mechanical advantage, MA is equal to 5. Now, say you actually use this ramp to push in 100 Newton crate up to the top with the real friction included. Instead, it actually takes 30 newtons of force to get there. So MA is equal to, the efficiency, sorry, not MA. So the efficiency is going to then equal 100N times divided by 30N, which is 3.33. Now, if you compare that to our ideal, which is here, ideal, so our ideal MA of 5 would be this. So efficiency of actual mechanical advantage, actual MA, over ideal MA. Our actual was 3.33, and our ideal was 5, and that gives us 66.7%. So also, by the way, if you don't know how to do your percentages, you just do this division times 100%, and that'll give you your percentages for those who, need a quick basic math review. So 66.7%. So that means the ramp is running at an efficiency of 66.7%. So it's a little over a third of your extra effort compared to the ideal case, basically. So understanding how all of this works together and doing practice problems will help you in the end. All right, and now we can go on to thermodynamics, which is chapter 3. Okay, everyone, so thermodynamics, if you haven't reviewed general chemistry, then learning general chemistry in tandem with sorry, I'm just blanking out. Thermodynamics is also studied in general chemistry, so if you learn in tandem with physics, that's really helpful. And anyway, the chemical physical section, CP section of the MCAT is practiced together, or it's examined together, basically. So learning them also in tandem can be useful because this same material is covered in chemistry. So anyways, let's just do some quick review anyways, but if it's still confusing, visit the general chemistry video that I already have. And then once you master like general chemistry, physics is a good next move to kind of do afterward. So what are systems? Systems are what we will be studying. So like, let's go through what systems are first. So there's 3 types of systems. You can have an isolated system, closed system, or an open system. And then systems can go through they have functions. So process functions and state functions. So isolated systems do not exchange matter or energy with their surroundings. So let's say a system is anything you're observing. So this is your system, for example, and the environment is anything around it, right? Or your surroundings is anything around it, really. Closed system exchange energy but not matter with their surroundings. Open system exchange both energy and matter with their surroundings. So the most commonly confused pair everyone makes at first is an isolated versus a closed system, and it's because they seem very similar, like isolated and closed. Both sound like nothing is about to get out of the system, but remember that a closed system still lets energy out. It's able to exchange energy. So really remember these definitions well. And now for temperature and the zeroth law. Did I want to go through processes right now? I mean, we could just go through them quickly so you understand it. Let me think about how I want to do that. Yeah, we'll go over it after as we learn about processes over here. So let's go into our temperature and the zeroth law first. So, and then I'll go back to these functions in a second. So the zeroth law of thermodynamics is basically temperature isn't just some mystery quantity. Temperature is like a direct quantity to tell you how much the individual particles in the substance are jiggling around. And so the exact definition is the average kinetic energy. And when systems have average kinetic energy that is equal, there will be no heat transfer between the two. So let's say you have a hot water going into a cold water, right? If your systems were in equilibrium, then there would be no heat transfer. But since the hot water is hot and the cold water is cold, they're different in average kinetic energy, or in other words, they have different temperatures, right? So because the hot water is different temperature from the cold water and you're mixing it, there is going to be heat transfer. But when you have thermal equilibrium, there will be no more. So once the hot and cold water have equilibrium and they're the same temperature, there would be no more heat transfer. And heat likes to go, it likes to travel like hot to cold, right? So temperature, again, is the average kinetic energy of the particles that make up the substance. So yeah, and then you have to know conversion. So you have to know, we have Fahrenheit, we have Celsius, and we have Kelvin. So if you figure out and have, let's say you're given Fahrenheit and you need to use Celsius, or you need to basically find the answer in Kelvin. Kelvin is very important, right? So a lot of the time you're going to be converting Fahrenheit to Celsius, and from Celsius, you can then convert Celsius and get Kelvin, right? So there's different units of temperature, but Kelvin's really important. So to be able to convert from Fahrenheit to Kelvin, you need to know, how do I convert Fahrenheit to Celsius and then Celsius to Kelvin? So yeah, unit conversions for temperature. Those are important to memorize. And then for thermal expansion, it describes how the substance changes in length or volume as a function of change in temperature. So temperature can change the length of something a lot. And that's a mnemonic that's not written down here, but people like it, where delta L is equal to the change in length. Temperature can change length a lot. So it looks like the word a lot, kind of. So you can kind of memorize the formula that way. And then delta volume. So volume can also have change a lot with changes in temperature. So the formulas look very similar, by the way. This one's just L and this one's just V. Okay. What else do we need to know now? We're gonna go over, I think I want to go over heat. Yeah, let's go over heat. All right. Okay, so here is the thing about heat. So heat is the process by which energy transfers between two objects at different temperatures. So remember, we just talked about the hot water and the cold water and stuff. So heat isn't a substance an object contains. Remember this, it's a process. Heat is a process, a transfer of energy. Heat is a process, transfer of energy, energy transfer here between two objects at different temperatures that occurs until the two objects meet thermal equilibrium. And until they're both the same temperature, that's basically what it means to be at thermal equilibrium, then you will have no more heat transfer. So Q equals MCAT is very important. So you notice another mnemonic or kind of memory tip that people use is Q equals MCAT. And it kind of looks like the word MCAT, so that might help you memorize it. So yeah, Q equals MCAT. So where Q is equal to, Q is a symbol for heat. So heat is always shown as Q, like that. That's heat. And then M is mass. C is a specific heat, which is going to be explained down here. Specific heat of water is always 1 calogram per Kelvin, or 4.18. So specific heat, what that is, which is C in this formula, C, is this amount of energy necessary to raise 1 gram of substance by 1 degree Celsius or 1 K. So this is the specific heat of water, which might show up. So sometimes they won't give you the specific heat of water, which is why you have to kind of memorize the specific heat of water. Otherwise, if you have a different substance, they might just give it to you, the variable. So yeah, that is specific heat. And that's your heat formula. Okay, and then we have heat of transformation. So heat of transformation, Q equals ml. You're thinking, okay, we have a heat formula over here, and then we have another heat formula over here, Q equals ml, right? But this heat formula is a little bit different. So if you look at heat of transformation, which is the energy required for a phase change of a substance, that is what the heat of transformation is. So this is a little bit different. So the heat of transformation is equal to L over here. Temperature does not change during the transformation. So is there a heat graph here? I'm going to show a heat graph. One sec. All right, so I just typed in heat graph, quite literally. You just type in heat graph, you get this. So look at this heat graph. So as you have an increase in energy, this one is good too. Yeah, so as you have an increase in energy or increase in time, and then an increase in temperature, your solids and liquids are changing phases. So solid can change a phase into a liquid. And notice that during the phase changes, the line is flat, right? So when S to L, when solid to liquid is happening, the temperature curve is not, it's not a curve, it's flat, right? So you notice that it's flat. So the energy required for phase change of a substance is the heat of transformation. Temperature does not change during transformation, as I showed you in the So from solid to liquid, for example, we're melting, it's flat. Temperature is flat, right? So L, is the heat of transformation. So it's very similar, but it is different. So the heat needed for a phase change is what we're looking at. This is the heat required for a phase change to occur. Okay, and this is about heat transfer until something hits thermal equilibrium. Okay, and then you have processes with constant variable. So you have isobaric, isothermal, adiabatic, and isovolumetric. So the first law of thermodynamics is important before we go into this, because I'm going to explain this with the first law, because you'll need to know what P, U, and Q are, which is part of the first law. So the first law of thermodynamics is a statement of the conservation of energy. So the total energy in the universe can never decrease or increase. For an individual system, delta U, which is the change in a system's internal energy, is equal to energy transferred into the system as heat. So this is heat. Q is heat, as always, minus the work done by the system. So W is this work. All right? So that's the first law of thermodynamics. And so the formula for one system is exactly that. The change of its internal energy equals the heat added to it minus the work that the system does. Okay, so whatever is left over changes the system's internal energy balance between the heat and the work, right? So when you go back to state and process functions, right? We're going to go back to that right now. So state and process functions. So when you have a state function, it's like, okay, imagine hiking up a mountain. Your altitude doesn't care which trail you took to get there. So it doesn't matter how, this is your mountain, and you did up to this peak here, and you climbed up to the peak of the mountain. Now, imagine all you cared was the height, right? Not anything, not about the path it took there, how steep the path was. So altitude is kind of like the state functions, where it's path independent. It just cares about the endpoint. So those state functions include pressure, density. Density is usually this little p, not d. Temperature, volume, enthalpy, internal energy, we just saw U. Gibbs free energy is G. Enthalpy is H. Sorry, I forgot to write that. Enthalpy is H. Entropy is S. And that's all of the examples for them. So if you don't understand what those mean, this is basically like chemistry review, so go back to general chemistry and learn that again. And then now process functions, think about the distance that was hiked. Like how steep was that hill? Was it like that or was it like that? Right? Did you climb this way, or what was the path like? And so the process functions consider the path from one equilibrium state to another. So that includes work and heat. So that's why we're saying work and heat here. They are path functions. Process functions, sorry. Or you can think of them as path functions as well. So work done by expanding a gas is W equals negative P delta V. So you can picture a gas trapped in a cylinder with a moving piston. If that gas expands, it pushes the piston outward, meaning it's doing work on its surroundings, and that work equals the pressure the gas is pushing against times how much of its volume has increased. So if there's no change in volume, if the change in volume is equal to 0, that means the gas did no work, so then work is equal to 0, right? So do some practice questions to help you understand better about those ones. And now we can get into the 4 special processes, which is what we were about to go over: isobaric, isothermal, adiabatic, and isovolumetric, also known as isochoric. So in these processes, you have a variable that is constant. So each of them simplifies the first law equation in its own way. So all of them will affect this first law equation here. There's too much going on here, I know. So let me just like remove all of this. My bad. I write too much, don't I? So all of these will end up affecting this first law of thermodynamics. So to be isobaric means that pressure will stay constant. So delta P is equal then to 0. So if delta P is equal to 0, we could simplify to W equals P delta V formula without pressure changing partway through. So pressure is equal to 0. That can be related to this as well. Basically, isothermal temp is constant. So delta U is then equal to 0 when temperature is constant. So since, for example, a gas's internal energy depends only on its temperature, holding the temperature means delta U is equal to 0. So the first law would simplify to Q is equal to W. Yeah, so every joule added of heat leaves as work, and every whatever work is then equal to Q, right? Adiabatic means 0 heat is exchanged. Like there's no heat exchange because Q is equal to 0, right? So the first law then becomes delta U is equal to negative W. And you can find this just by subbing this in, right? If you sub in delta U, Q, right? And then delta V is equal to 0, where no volume change. So this is what I was just going over for isovolumetric, that let's say you're calculating the work of a gas and you sub that in. Work is equal to negative P delta V. If delta V is 0, because it remained constant, then that means no work would have been done. W also equals 0. So that's why in an isochoric, it says, as it says here, delta V is equal to 0, so work is equal to 0. You can just sub that in. And these ones, you can sub those into their pressure here. You could sub that into here, and that'll give you a simplified equation. All right. So that's everything about heat and first law of thermodynamics, which is awesome. And then here's a pressure volume graph. Just know these and what they look like. Why does it look like this? So volume stays constant in isovolumetric, that's why it's straight line. Isobaric, the pressure is constant, so that's why this is a straight line this way on the y-axis. So the y value stays the same, which is absolute pressure, right? Pressure is on the y. And then x here is staying the same for volume for isovolumetric, so that should make sense according to our definitions. Isothermal has a curve going decreasing as the final volume increases. So pressure goes down, right, as volume is going up, right? So that's isothermal. And then adiabatic is the same thing, but less steep for adiabatic. Okay. And then sometimes if it helps you, you want to ask why, and that can help you learn deeper understanding. It might help you later for practice. Okay. And so that's how you read a pressure volume diagram. And then we can go into the second law of thermodynamics. So in a closed system, right, up to and including the universe, energy will spontaneously disperse. So if you ever seen yourself spray a spray into the air, the particles of the spray diffuse out, right? And so the particles like to be in high entropy. They don't like to be like solid and structured like this. Naturally, things diffuse and they actually they end up looking like that, right? So that's kind of how I think of it. So the second law states that, and so if you don't understand what it means, spontaneously and irreversibly is related mostly to general chemistry. Here are some terms from general chemistry. So going back to review that if you don't understand is important. Entropy is usually, there's also a formula for it. Usually the variable for entropy is S. And it's a measure of how much energy has been spread out. So if S is really high, then you have high entropy. If S is really low, then you have low entropy. All right, so that is the second law of thermodynamics. And Yeah, that's about it. And so they also have a picture to contrast open and closed system here for anyone who's more like a visual learner. But you can also search up a picture that might help you anywhere on Google, really. So that's chapter 3. And then next thing, we're going to go into fluids next. All right, so now let's do our review on fluids finally, chapter 4. So this is about, obviously, fluids. So you have to understand what are fluids anyway in the first place. So fluids are any fluid substance is basically anything that can flow and can conform to the shape of their container. So imagine you pouring orange juice into your cup. It conforms to the shape of that container. So that would be considered a fluid, right? But it also includes gases, by the way. So it might surprise you that fluids would contain gases as well, but fluids can also contain liquid. They can be considered liquids and gases, right? Sorry. That was loud. Liquids and gases, they can exert perpendicular forces but not shear forces. So right, so if you pour water into a cup, it becomes cup shape, but if you pour it into a bottle, it becomes bottle shape, and etc. So now, if you compare that to a solid doesn't flow. Solids don't flow, they maintain their shape regardless of their container. And there's one more thing to note, that only perpendicular to the surface or straight to it is what fluids can push on things. So only perpendicular, not straight into it. Wait, sorry, perpendicular is straight into it. So they can't really resist being sheared or slid sideways, which is what a solid can do. So solids can flow, like, you can think of more parallel, sliding an ice cube parallel to a surface, whereas fluids are exerting their force against the walls of the container. So perpendicular. This is parallel, and that's perpendicular. All right, and so density is how packed something is, right? So mass per unit volume of a substance, and you have to know the, so it's mass over volume. That's what density is. Density is this little p in the formula, and so that's basically density, how packed something is. And then pressure is important to remember. Pressure is equal to the force over the area. So if you ever push something on a small area, right, you're pushing that, like the point of a thumbtack to get, pressure on like a thumbtack to get it put into the wall, for example. If you spread that exact same force over a flat area, right, it's like pressing your whole palm. You barely leave a mark. So same force, totally different pressure because the amount of area has changed. So the amount of pressure changes with the amount of area that you apply, right? So pressure is what a fluid exerts on the walls. Remember I talked about the walls of the container, holding on it, and anything sitting inside of it. And so the neat rule is that whenever fluid pushes on something, it always pushes straight into the surface perpendicular to it. So that's what we were reviewing up there, right? So absolute, this is what it says, perpendicular to container walls. Okay, so absolute pressure, it can be contrasted with gauge pressure. So there's a difference between the two. So absolute pressure is where people might get confused. So just imagine you're at the surface of a swimming pool. Even before you touch the water, there's already air pressure pushing down on everything. And we call that atmospheric pressure. So just by, living, and then there's water, there's already atmospheric P at PATM, pressure, atmospheric pressure, is equal to the pressure at the surface plus density times gravity times height. So, absolute pressure is the total of everything, the atmospheric pressure plus the pressure added by the fluid itself. So it's nice to know that basically that if you want an example, right, in water, every extra 10 meters you go down adds roughly 1 full atmosphere of pressure. So at 10 meters underwater, you're not just dealing with the air pressure from the surface, you're basically double the total pressure on your body. And that's why deep sea divers need special training and gear, because the pressure that happens when you go lower and lower and lower in the sea is high. The pressure is very high. So that's how you can think of the formula here. All right. So now we can go into gauge pressure. So gauge pressure is a more simpler idea because it's just the extra pressure that's on top of the atmospheric pressure. So it's not the P total, it's P minus P ATM. Right, so it's what you have for the P total minus atmospheric pressure. So it's whatever pressure is without atmospheric involved. That's basically it. And then hydrostatics, right here. Hydrostatics. So we're moving into a branch called hydrostatics, which is literally still fluids. So fluids that aren't really moving. This is all about fluids that aren't flowing anywhere. They're just sitting there and the forces that they create. So for Pascal's principle, it's basically if you apply pressure to an incompressible fluid, meaning that the fluid, so incompressible fluid, it means that the fluid can't be squeezed smaller, Like water, that pressure spreads out undiminished through the entire fluid. So every part of it feels the same pressure equally, so undiminished throughout the entire volume. So pressure is kind of equally felt by every part of the fluid. So why does that matter? Because it lets you build machines, hydraulic machines. It lets you build machines that multiply the force. Okay, so you can think about a car lift at the mechanic shop. So you push down with a small amount of force on a narrow piston that creates a certain pressure. And since pressure is the same everywhere in the fluid, that same pressure acts on a much bigger piston on the other side. And remember, pressure equals force over area. So if the area on the other side is huge, the force on that side is huge too, right? So even though you only push lightly on your end, right? So that's how a single person can lift an entire car with a hydraulic jack. You're not like doing anything special, but what you're doing is you're trading a small force over a long push for a giant force over a short push. So it's just the same pressure, it's just being redistributed. So hydraulic machines can help. And it leads to a mechanical advantage. And so we already reviewed mechanical advantage before in, chapter 2 for work and energy. So if mechanical advantage is still confusing, going back to the chapter can help. Okay, so Archimedes' principle is explaining like why do things float. So we're gonna end up talking about buoyant force. So why do things float? So this comes from the Archimedes principle. So when you put any object into a fluid, that fluid pushes back up on the object with a force called buoyant force. And here's the elegant part. So if I draw my little floaty, there's buoyant force pushing up, right, against the object. That is equal to the weight of the fluid displaced by the object. So basically, what we're trying to figure out with this Archimedes principle is, like, if you have a practice problem, it might ask you, will this something float or sink, right? It comes down to the two forces, gravity pulling the object down and buoyancy that's pulling it up, right? We just learned buoyant force. So if the maximum possible buoyant force is bigger than the gravity's pull on the object, then the object will float, right? Buoyancy, if buoyancy is higher than gravity, then the object will float. If the buoyant force is less, then you're going to sink, right? Because gravity is going to push down, and it's going to cause sinking. And if gravity is a greater force than your buoyant force, then you're going to sink to the bottom of the sea, like SpongeBob. Okay, sorry. Yeah. And so this is related to the idea of specific gravity. So for specific gravity, it's just the ratio of an object's density to the density of water. And the density of water, you should probably memorize, is always 1, basically. Yeah. 1 gram, the unit is 1 gram centimeter cube for water. That's water's density usually. Okay, so memorizing water's density can be helpful for you when you're problem solving, and this is the ratio. So it would be the density of the object over the density of water. So if something has a specific gravity less than 1, then that means it's less than water. So it will be less dense than water, right? So if it's less than 1, if SG, specific gravity, is less than 1, then that means, right? That means your specific gravity is less, your density of the object is less than water, and so you get float. You get something that will float. But if an object has a lot of density, right, it's on the water, and it has a lot of density, then it's going to end up sinking if the density is higher than water. So specific gravity has a lot to do with understanding as well whether an object will float or sink. So these two ideas are related. For cohesive versus adhesive, and also surface tension. So these are some quick vocabulary terms to know, right? So cohesive forces are forces, it's about the attraction between molecules of the same fluid. Water molecules sticking to other water molecules, for example. Adhesive forces are attraction between a fluid and some other material such as the glass, right? And so the cohesive forces will create surface tension. So I'm going to show a picture of this, actually, it's better. Okay, someone drew this diagram here, it's kind of nice. So yeah, cohesion and adhesion. Cohesion, same molecules attracted to each other. Adhesion, one molecule attracted to another substance. So adhesion would be water attracted to the glass. So this water is attracted to the glass, so it's creating this shape here. And then cohesion is water being attracted to water, right? Okay, so that's a good diagram. Now we can go over surface tension as well. So did we go over that yet? I don't think so. Yeah, so cohesive forces give rise to surface tension. So when cohesive forces essentially dominate at the surface of the liquid, you get surface tension. And so that skin-like effect on the top of the water you notice sometimes, that lets a water bug like glide on top of the water in those instances because there's surface tension. Or it can let, for example, when you slightly overfill a glass of water before it spills, it has that surface tension on the top. Right, so I have a cup here, right, and then I filled it to the top. It has a slight, like, surface tension, and that's due to cohesive forces of the water sticking together before it breaks apart and spills over. Okay, let's go into fluid dynamics and fluid in motion. So the first thing is viscosity. I always think of honey when I think of viscosity. Viscosity is like how thick and sluggish something is, as what I learned in science class. So this is basically the measure of a fluid's internal friction. Viscous drag is like when a fluid experiences this internal friction as it moves, it's called viscous drag. So if you like pour a lot of honey onto a glass, you notice that the honey moves very slow and it's so thick, right? So that's something that has high viscosity, or it's very viscous is what we would say. And so a viscous drag is a force that saps energy out of the system. So energy gets out of the system rather than storing it. So laminar flow and turbulent flow. This is relevant as well to weight. This is kind of relevant when you're doing like how speech is made for human voices, because our human sounds are made by a turbulent flow with our mouths and our the way we shape our mouths and stuff create a turbulence of air, and that turbulence of air then allows us to say words like pa, ta, right? What else am I gonna say? Okay, definition, sorry. Laminar flow is smooth and orderly, so it just goes like this in a straight, smooth line. Whereas turbulent flow, okay, let me get a picture, because there's definitely pictures I can find of laminar and turbulent flow. So yeah, this is a good picture. Now we can move on from those two. So Poseidon's law, like Poseidon, the Greek god, there's this law that tells you how fast a fluid will flow. So the rate of laminar flow, there's something like a tube. So the tube will allow laminar flow as long as the tube doesn't have any obstacles in it. So this is a picture of like pretty laminar flow down here as well. So Poseidon's law is the flow rate is equal to area times that's my flow rate down here. My bad. So Poseidon's law is Q. So Q is equal to pi R4 delta P over 8. This is a viscosity, I believe, times L. So it's like, what is this, right? Here's one thing you need to remember. The flow rate depends on the radius of the tube raised to the 4th power. So you see this R to the power of 4. And this means that if you narrow a tube just a little bit, the flow rate drops off dramatically. So this is huge in medicine because it's a part of why even like small amount of plaque buildup, narrowing a blood vessel, for instance, can dramatically cut down blood flow, right? So a tiny change in radius creates a massive difference in flow rate. So Q and R, 4, right? Okay. And so flow rate, so you don't have to know this too much. Remember the formula and how things affect different things. So the relationship between radius and pressure gradient is inverse exponential to the 4th power. So that's an important relationship that's highlighted. So flow rate. Flow rate is area times velocity, right? So let's say that your flow rate is just like how much volume of the fluid passes at a point per unit time, and also equals the cross-sectional area of the pipe times the fluid's velocity. So now there's a rule also called continuity equation, right? So continuity equation explains something you felt with your own hand. So put your thumb over the end of a garden hose, right? And have you ever seen that by doing that, it creates like the water shoots out so fast because you're creating a narrow passage. So if you ever seen fluid go through a more narrow passage, it's like really shooting out water really fast. So the continuity equation says that for a fluid that isn't being created or destroyed along the way, whatever volume flows in a more narrow section per second, has to equal whatever volume flows out of a wider section per second. So since the tube got narrower, right, the only way to keep the same volume of like water moving out is to push more water out faster. So narrow passage is very fast flow rate for the water or whatever liquid. So a wide passage, right, will have a slow flow rate, and that's basically the continuity equation here. Okay, so yeah, so if you change this, velocity would change with this cross-sectional area. And yeah, if you change it would change the new velocity and area. So if my area were to decrease, right, less area, then then you would have that relationship, and then Q right here, Q is the rate. Okay. Anyway, I'm a little bit tired, but let's move on to Bernoulli's equation. Sorry. So this is a famous idea. So it says that basically, like as a fluid moves through a closed system, we already reviewed closed system, right? So fluid is moving, and the sum of its static pressure, so the regular pressure sitting in the fluid, and its dynamic pressure, static and dynamic, which is dynamic pressure is related to the motion and speed, right? Plus height, right? Plus height stays constant at any 2 points along the flow. So the most important takeaway that you get from this is that when a fluid will speed up, its pressure drops. Remember I said that when a fluid speeds up, so if the fluid ends up speeding up, its velocity V1 speeds up, then the pressure on this side will drop. The new pressure will drop. This is for a closed system. So when it slows down, its pressure rises. Speed and pressure move in opposite direction. Speed, so V goes up, then P will go down. So they're basically inversely related. Okay, now we can go on to the Venturi effect. So if you have, let's say you have, let me think of something for a second. It's basically Venturi effect putting the continuity equation and these Bernoulli equation together, right? So the Venturi effect is when you say, when a fluid is forced through a constricted narrow pathway, right? Constricted narrow pathway. The narrow section of the pipe, its velocity has to increase, and we just learned that from continuity equation. But now Bernoulli tells us if velocity goes up, then the pressure also has to go down. So in that narrow section, even though you have this high speed narrow passage where the air is like traveling super fast along a narrower passage, the pressure, even though you have high speed, the pressure will go down. right, at the same time. So this is one of, like, it's pretty cool, and it can help explain why airplanes generate lift. But anyway, that's besides the point. That's a Venturi effect. So it's basically a combination of continuity and Bernoulli's equation explained. Okay, so now fluids in our own body. This is about fluids in physiology. So we're talking about our own body. So circulatory system, breathing, and alveoli. If you don't understand what those mean, then reviewing biology is important, because circulatory system is talked about in your biology as well as alveoli and how your breathing works. So if you've done biology before, then this would just be like review for you, basically. So your circulatory system, which is basically your heart, arteries, and veins, behaves like a closed system. Again, this is not like 100% review of biology, but if you don't know what your circulatory system is, breathing, or alveoli, then that can be a little bit of a problem. So just understanding those terms. I just defined it for you, right? Your heart, arteries, and veins. So it behaves like a closed system, meaning that the blood doesn't leave the system as it circulates, right? But unlike a steady, constant flow, your blood is not constant. It surges and then it goes whatever. It's like a pulse, right? And so every time you feel your pulse, you're literally feeling non-constant fluid flow around your heart's pumping cycle. Right? And so the same relationships we just learned about fluids kind of apply to your body. Velocity of blood equals the heart's output, so how much, divided by the cross-sectional area. So that's that formula. What else do we want to go over? The pressure difference across the system equals the cardiac output times the resistance of vessels. There you go. And so just like the continuity equation predicted with the pipes, when a blood vessel's cross-sectional area goes up, so let's say your cross-sectional area went up, right? So area went up. So that's basically saying your blood vessel is widening, then your resistance would go down. Resistance goes down. Resistance goes down. And so all these formulas help us relate what's happening. Pressure is directly related to velocity, area, and resistance. Area is inversely related to resistance and velocity. So if area went up, then resistance would go down, velocity would go down. If area went down, then velocity went up, resistance went up. Cross-sectional area goes up, resistance goes down, and our velocity goes down. So that's just saying what this said. And then for breathing, when you inhale or exhale, you're creating a pressure gradient. And so that basically explains how your body breathes in air. So you're not actually, I don't know how to explain it that well, but you're not actually breathing in air, but the air particles are naturally like trying to equilibrate a lot of the difference in pressure and the gradient. So yeah, when you inhale and exhale, you're creating a pressure gradient, and that doesn't just move air in and out of your lungs. It also affects your circulatory system, because your chest cavities, pressure changes affect the vessels that are running through it. And your alveoli, air at the alveoli has essentially zero speed. So by the time the air reaches your alveoli, the tiny air sacs deep in your lungs, so that's your alveoli, right? Where oxygen will actually, like, that's where oxygen exchange happens, or gas exchange for CO2 and then O2, right? If you don't know that part, then reviewing biology would help on the circulatory system and breathing. But anyway, that's where gas exchange is occurring at your alveoli, and so its speed has essentially dropped to zero. That's what it's saying. So all that momentum from breathing in gets absorbed by the time it reaches its final destination, because you want like a calm, nice environment, still environment for gas exchange to happen efficiently. So that is our entire block on fluids. Great. Okay, electrostatics and magnetism. I'm not a big fan of electrostatics, but you might be. So anyway, let's get into charges and the basics of what's going on. So every atom has protons, right? So which carry a positive charge. Protons have a positive charge and electrons have a negative charge. By the way, the unit for a charge is called coulomb. And so anyway, both protons and electrons possess the fundamental unit charge, 1.6 times 10 to the negative 19 coulomb. This is not Celsius or anything like that. That is coulomb. C is coulomb. Protons and electrons have different masses. So that's a very small amount, by the way, this number. Yeah. And then so for attraction and repulsion, right? This is probably something you already know intuitively, but opposite charges attract and like charges repulse each other. So if you have watched the video on, I think, biochemistry lab techniques about gel electrophoresis, it's connected to this idea, but if not, that's fine too. So anyway, if you have a positive and a positive, these will repel each other, is what they say, repel, or they just won't like be attracted to each other, but positive and negative will be. Okay, so attraction and repulsion. And then now for for conductors and insulators, not all materials handle charge the same way, right? So conductors are like most metals. So remember your metals on the periodic table from general chemistry. General chemistry, that would be like chapter 2, I think. Most conductors are mostly like metals, and so what they're able to do is they're able to let electrons spread evenly and move freely across the material, and that's why we use metal wires to carry electricity, because the charge just flows right through them. So they're really good at what its name is saying, conductors, so conducting electricity. Insulators, on the other hand, can relate this to myelin sheath. Myelin sheath in biology. So I'm trying to relate this to other subjects because they're all relevant to each other. Resist the movement of charge and will have localized areas of charge that do not distribute over the surface of the material. So on the other hand, insulators can be, for example, rubber or plastic, and so they'll resist the movement of the charge. So they're doing the opposite of what the conductors are doing. Yeah. So that's why when you like rub a balloon on your hair, the balloon is an insulator, so the charge that you rub onto it stays right where you rubbed it instead of draining it away. Anyway, let's go into Coulomb's law. Coulomb's law is next. So Coulomb's law is answering the question about how strong is the force between two charges. So if I wanted to know how strong the force is between two charges, and that's what the problem was asking me for, I would use the Coulomb's law formula over here, right? So it's basically force equals K times charge 1 times charge 2, the absolute value. So there's no negative, everything's positive. Absolute value is just like, if it's negative 2, then you just 2. Then you just use 2, sorry. Then you just use 2 for the absolute value. So if you don't know how to do math for absolute values, go ahead and learn about what absolute values are. Don't be ashamed to learn things over again. I never had to relearn that because I had a basics of math, but yeah, knowing your math and how to do it is important. Divided over distance squared, so r squared. So the distance is how far apart the two charges are. All right, so now we can go over electrical fields. So electrical fields is an important concept that builds directly on Coulomb's law. So you need to know Coulomb's law first. So the electrical field, right? So every single charge just by existing generates an electrical field, an electric field. And so it's like an invisible field all around itself in space based on that charge. So any other charge that wanders into that field will feel a force from it. And without, it's like they don't even need a touch, right? So it's just like a field of charge, invisible, you can't see it. So you think of an electric field as a kind of force per charge. So the electric field is equal to force on a test charge divided by the size of that test charge. Right, so you can calculate it directly from the source charge itself using basically the same structure as Coulomb's law, just without the second charge in it, because the field exists whether or not there's actually a second charge to feel it. So electric field will be there regardless. So every charge generates an electric field, and you would use this formula. Okay, field lines. Field lines, this is a good diagram too, are used to represent electric field vectors for a charge. So field lines, they're basically a visualization of the electric field, right? So the way to read them is you want to imagine a tiny positive test charge. So let me just get like field lines. So in a positive one, it radiates outwards, and then a negative one, the field lines radiate inwards, right? And this is them coming together, and so it tells you where the electrons would flow, and so the flow of the current flows away from the positive charges since they like to repel, and curve goes into negative charges since opposites attract. So as you can see, curves are going in, right? Okay. All right, so then you have special cases in electrostatics. So equipotential lines is like a line where every single point along it has the exact same electrical potential. So we'll define potential more precisely in a second, but for now, just think of it as a kind of electrical height, similar to how every point on the contour line on a topographic map is the same elevation. So the key concept or the key relationship is that equipotential lines are drawn perpendicular to electrical field lines. So they cross each other at perfect right angles always, right? And so here's a generally useful rule. If you move a charge from one point to a different equipotential line, that takes work. So you're either doing work on the charge or the field is doing work on it. But if you move a charge between 2 points on the same equipotential line, then there's no work done at all because there's no charge in potential to overcome, right? So this is related to work being done. Okay, so for electric dipole is simply when two charges of the opposite sign are separated by a fixed distance. Okay, so a field is created by something else. Okay, let's go back for a second. So you have simply two charges of equal size, but they have opposite signs. So plus Q and negative Q, right? Yeah, that's what I wanted to show. So yeah, plus Q and negative Q. And so an electric dipole, right? The two charges, opposite sign, but they're the same size. So let's say it's plus 2, minus 2. Sitting at a fixed distance apart. So R is equal to, I don't know, 5 meters apart, for example, right? Think of the positive charge and negative charge as a pair permanently locked at some distance from each other. If you put a dipole into an external electric field, a field created by something else, right? So any external electric field is just a field created by something else. This is what happens. The field exerts a net torque on that dipole, net torque on that dipole, meaning it twists the dipole around, trying to rotate it until it lines up in the direction of the field. So like you can think of a compass, right? It doesn't fly toward magnetic north. It rotates to the point, it rotates the point toward it, right? So a dipole in an electric field behaves the same way. It experiences twisting, not a straight line pulling. And so an electric field would never cause a dipole to physically translate or move over to slide from one place to another, right? But instead, it only ever spins it, spinning. So you have spinning. Spinning occurs. And that's how your net torque is. That's why torque is involved in this. Torque, remember, is about rotational spinning and stuff like that. Rotational movement. So the strength of this twisting effect is called the dipole movement. Or sorry, dipole moment. The strength of this twisting is called the dipole moment. So the dipole moment is the strength of the twisting effect. So if, for example, the charge side multiplied by the separation distance between the two charges. So if I had bigger charges, that's d for distance. So if I had really big charges, right, so charge size multiplied by separation distance, if I had really, really big charges, or a big gap, or a big d, charge, or q, between them, means you will have a stronger dipole moment. Stronger, also strong, right, because they're all moving proportional to each other. All right, so now we can go into electrical potential energy. So one way you can imagine this is like, imagine you have a fixed source of a charge sitting in some space, and then imagine you bring a second test charge in from far away, from so far away that it doesn't feel any force yet, and then you keep moving that other charge closer and closer, all the way to some specific spot near your source charge, or your first charge, whatever. So the electrical potential energy at the final spot is defined as the amount of work it took to bring that test charge there. So whether the energy increases or decreases, right, whether it increases or decreases, so whether that happens depends on entirely the two charges, whether those two charges like each other or not. So if you're bringing like charges together, both positive or both negative, so positive, or if it's a negative, that those situations, opposite charges move apart. Again, we learned that about attraction and repulsion already over here. So opposite charges move apart, and then like charges, why does it say move apart here? I think there's a typo, to be honest. So you have to do positive work and potential energy increases for like charges. If you have opposite charges, they're pulling toward each other and doing a lot of the work for you. So potential energy actually decreases, right? So potential energy would decrease because the opposite charges are like each other. So they're already attracted to each other. So you don't have to do a lot of work to bring them close to each other, right? Okay, so I don't know what happened here. I think there's a typo here. Like charges should not be, wait, no, opposite charges. Okay, now it's even confusing me, but there's a typo. Okay, be careful, beware. Okay, electrical potential now. So this is also known as voltage. So voltage, this one trips people up, so we can go a little bit slower. Electrical potential is simply electrical potential energy per unit of charge. So in other words, if you take that potential energy that we just talked about and divide it by however much the charge you're talking about, like given to you, this gives a property of a location in space, a number that tells you the potential at that point, independent of how big a test charge you use to like measure it. So because different points in space around a source charge are at different distances from it, they naturally have different potential values. So we'll have different electrical potential values. Kind of like how different points on a hill have different heights, right? So the unit for potential values is volts, so V, and 1 volt is equal to 1 joule over C, which is coulombs. Sorry. And then a voltage is the potential difference. So people can sometimes mix up voltage. So voltage isn't a single point's potential. It's the difference in potential between 2 points. This is what we have, the difference in potential in between 2 points. This is exactly what a battery does. So your standard 80 battery creates a 1.5 volt difference, for instance, between its two ends. And that difference is what pushes the charge through the circuit. So for test charges, how do those behave? So for test charges, basically a simple rule that ties together electrical potential and the potential energy is that any, how do you say this? Any charge left alone will spontaneously move in whichever direction causes its own potential energy to decrease. So nature always seeks to be the lowest energy option, like a ball rolling downhill, right? So it likes to be the lowest energy, but and this is the part that kind of messes people up sometimes. The direction that means for potential, not potential energy, depends on the size of the charge. So a positive test charge will spontaneously move from a region of high potential toward a region of low potential. But a negative test charge does the opposite. It moves from, so this is negative test charge moves from low potential to high potential. So why does this happen? Because for a negative charge moving toward high potential is actually what decreases its potential energy. So remember, potential energy and potential are not really the same thing. Remember that once you factor in the sign of the charge doing the moving. Okay, for magnetism, we have a magnetic field, not an electric field, a magnetic field, which can be created in two ways. So you can have permanent magnets that created by magnets and also moving charges. So anytime charge is in motion, like electrons flowing through a wire, it creates a magnetic field around itself. And this is a link between electricity and magnetism. So moving electric charge literally creates magnetism. So the SI unit that's used is Tesla, T, which is also equal to 10,000 Gauss. So if you have a straight current carrying a wire, the magnetic field it forms, the magnetic field looks like circles, essentially, wrapping around the wire. So picture rings around a cylinder getting weaker the farther out you go from the wire, but the closer in the wire, it's really strong. And then we have diamagnetic, paramagnetic, ferromagnetic. So this is like chemistry review, but we're doing it from a physics perspective. So diamagnetic materials have no unpaired electrons, and as a result, they are weakly repelled by a magnet. So if you didn't understand that just by me saying that, then doing review on general chemistry would help. Gen Chem would help. I forgot exactly what chapter was reviewed. I think it was actually chapter 1 with diamagnetic and paramagnetic, and even ferromagnetic wasn't really talked about here, but you should learn them too. So ferromagnetic is when you possess some unpaired electrons and become strongly magnetic in an external magnetic field. Paramagnetic, some unpaired electrons become weakly magnetic in external magnetic field, and diamagnetic, no unpaired electrons slightly repelled by a magnet. All right, so that is that. If this doesn't make as much sense, you should go back review Gen Chem. So how do magnetic fields push on charges? So what's important to remember about magnetism is that a magnetic field can only push on a charge if that charge is moving and moving in the right direction. So specifically, an external magnetic field will exert a force, moving on a it will exert a force on a moving charge in any direction, right? So except if the charge happens to be moving exactly parallel or exactly opposite, which is anti-parallel to the field itself. So in those two specific cases, so parallel or anti-parallel to the field. So in those two specific cases, there's no force that happens at all. Okay. So if a charged particle moves in a uniform magnetic field at the right angle, the magnetic force acts as a centripetal force. That's why we were learning about centripetal forces, right? The inward force needed to keep something moving in a circle. And the particle ends up curving in a perfect circular path. So yeah, it's like a string pulling it around and around. Remember centripetal force. So to figure out the direction that it points, right, we are using two main formulas. So for a single moving point charge, the magnetic force depends on the size of the charge, how fast it's moving, how strong the field is, and the angle between the charge's velocity and the field's direction. For a current carrying wire, the force depends on the current flowing through it, the length of the wire, L, B, the field strength, and again, the angle. All right, so in both cases, notice that angle matters. One sec. Sorry, I had to sneeze. Lorentz force is finally the last thing we're going over. I think that was it, right? Yeah, so Lorentz force is the last thing we're going over. And so this isn't a brand new type of force. It's simply the total force on a charged molecule. So the sum of electrostatic and magnetic fields acting on a body. So the total force on a charged particle, when you add together the electrostatic force and magnetic force, electrostatic would be any electric fields present, and magnetic force would be any magnetic fields present. So that's why I kind of went through it last, because it's basically literally the sum of electric fields and then the sum of magnetic fields, and that's Lorentz force. Yeah. And then here are essential equations to know on test day. So these are equations we already went over. All right, so now we can go over circuits. Circuits kind of has a nice kind of flow into from what we were learning before about the electric field. So now we're learning about circuits, right? So we can start off by getting to know charges and current. So current is simply the movement of a charge between 2 points that have different electrical potentials. So remember, potential is basically like saying electrical height. So current is charge flowing from a high point to a low point, like a water flowing downhill. Now, this is kind of like some history for everyone. Current is interesting. By convention, we define current as the movement of a positive charge flowing from the high potential end of a voltage source to the low potential. But the twist is that in reality, in almost everyday, every circuit that we see now, it's actually electrons which are negatively charged that are physically moving, and they move the opposite way from low potential to high potential. And so we still talk about current as if it were a positive charge moving forward, and you can think of it as positive flow. That's how I think of it. Positive flow. And so scientists, it's just out of pure convention from back then, but scientists picked a direction before we even knew that electrons existed, and so we ended up just sticking with that definition. And it doesn't change any math or the physics, it's just something to be aware of, that conventional definition of current flows one way, but the electrons doing the actual moving are going the other way. So electron flow is very different from current flow. It's the opposite. So you can think of current as positive flow and electron flow as negative flow. So in reality, it's negatively charged particles, electrons, that move in a circuit from low potential to high potential, whereas the movement of positive charge, or the current, positive flow, moves from high potential end of the voltage source to low potential end. So that's what we have there, and that's the formula to know. Okay, now we have, current. Yeah, so current equals charge over time, or the difference in time, delta T. Now we can get into conductive materials, which we already learned about technically, but we're going to learn about it in more detail. So metallic conduction, electrolytic conduction, and insulators. So metallic conduction is what happens in wires and metals. It's current caused by the flow of electrons, and electrolytic conduction is different. It's the movement of free-flowing ions, so charged atoms or molecules under an electric field, which is what happens when things like batteries or salt water. And of course, insulators don't even conduct current at all, so no conduction of current. And then we have Kirchhoff's law. So when you start connecting multiple wires and components together into an actual circuit, you need some rules to be able to track everything. So that's where Kirchhoff's laws come into play. And really, they're just two common sense ideas about conservation with a bunch of formal language about it. So junction rule and loop rule. So your junction rule is stating that at any point where multiple wires meet is called a junction. Where multiple wires meet, that is called a junction. Kind of like your neuromuscular junction in biology. In your muscle system. That's kind of like what a junction is too. And so whatever current flows into that junction must be equal to whatever current flows out of it. That's what it's saying. So nothing ever gets created or destroyed. Charge simply has to go somewhere. And then for the loop rule is basically if you trace any closed loop in a circuit, you can imagine, for example, you're walking in a full circle following the wire. The total voltage supplied by sources like batteries around that loop always has to equal to the total voltage used up or dropped by components like resistors around that loop. So energy in equals to energy out. So all of this is about energy is never created or destroyed. It's just transformed or going somewhere. It's not, anyway. So energy in equals energy out for this one. All right. So what else do we want to go over? Resistance, because we were just talking about resistance, right? So resistance is the opposition that a substance offers to the flow of electrons. So it's basically, resistance is the opposite direction of where the flow of electrons will be going. So some materials let electrons go through really easily, so they'll have low resistance, and other materials will make it hard for electrons to get through, and that means it has a high resistance. So a resistor is a type of material or component made from a conductive material that has a moderate amount of resistance, enough to meaningfully slow down any electrons without stopping them completely. So here's the formula. Resistance equal to resistivity times length divided by the cross-sectional area. And so Ohm's law is the next relationship where voltage is equal to current times resistance, right? So basically, for any given resistor, the amount of current flowing through it is directly tied to how much voltage or how much potential push, basically, you apply across it. So if you push harder, meaning you have more voltage, right, more current will flow. And then you can add more resistance, and for that same push, less current gets through. And so this is basically showing that relationship. So again, for given resistance, the magnitude of current through the resistor is proportional to the voltage drop across the resistor. All right. So now we're getting into resistors, seeing them in series and parallel. So it helps to see this in diagrams. So make sure you look at the diagram. So this would be resistors in series, and this would be resistors in parallel. So for the resistors in series, right? So basically, real currents usually have more than one resistor. So they're connected together. So we see resistor 1, 2, and so on and so forth. So resistors, you can just add them up, and that will give you the total resistance, so just by adding them up. And then for parallel, you would have to do the reciprocal and add them up to get the resistance number. And the same thing goes with capacitors. So in the capacitor in series, it's actually what you have to do is you do reciprocal in a series, but in parallel, you just do C plus C1 plus C2, etc., etc. And you can find the total capacity that way, C total. So then we can finally go into capacitance and capacitors, since we kind of introduced that a bit. So capacitors is a device with the ability to store and later discharge electrical potential energy. So store, discharge electrical potential energy. So think of it as a tiny, fast-acting, rechargeable battery. It works on a totally different principle. So instead of chemical reactions, a capacitor typically works by literally piling up positive charge on one plate and then negative charge on another, and then separated by a small gap, with the electrical field between those two plates being where the energy actually lies. So a capacitance is where you have a measurement of exactly how much charge a capacitor can store for a given amount of voltage applied to it. So capacitance is equal to charge divided by voltage. For the simplest common design, you have capacitance, which is a constant, times the area of the plates divided by the distance of the plates. So the bigger the plates are, right, you can store more charge because there's simply more surface area for the charge to spread across. And the plates that are closer together also increase in capacitance because the electric field between them, and therefore like the traction pulling opposite charges toward each other across the gap gets stronger. So inside a capacitor, the electrical field is simply voltage divided by the distance between, whoops, why am I drawing it like that? Electrical field in a capacitor is voltage over distance. And then potential energy of the capacitor is this formula here, U equals half CV squared. So that's what you get for that one on the potential energy. What else did I want to say about it? We already went through series and parallel down here, but yeah, you can have series and parallel. Capacitors that are in series have lower equivalent capacitance of a circuit. Parallel, or the sum of the other, create a large equivalent capacitance. So this, what we saw here, is related to these images here with their formulas. And then what else do we need to go through? Dielectric materials. So one important concept is dielectric materials. These are simply like insulators that have been designed to be placed in a gap between capacitors' two plates. And because the material is an insulator, it doesn't let charge leak across the gap. And so it does increase the capacitor's overall capacitance, right? So increased capacitance by a factor equal to the material's dielectric constant. Sorry, dielectric constant. And so the more that the material boosts that capacitor ability to store charge, it means that there's a bigger dielectric constant, just by like sitting in the gap between the two plates. That's what it could do. And so meters is the last thing. This is basically kind of like measurement to measure what's happening. So ammeters are to measure current, right? So measure current, and they have negligible resistance. So you can think of this, they're inserted directly into a series with the part of the current you're measuring. And so the current has to physically flow through the ammeter itself for it to be able to measure. And so for this to work without disrupting the current's behavior, ammeters are designed to have negligible resistance, or else if they did have resistance, then it would then impact the current and then you couldn't measure it properly, right? And then for voltmeters, it's inserted in parallel circuit to measure a voltage drop, and they have very large resistances. So voltage, the potential difference between 2 points, they work the opposite way. So voltmeters are opposite, right? They're inserted in parallel, connected alongside the component you're measuring, rather than directly in its path. So for this to work properly, voltmeters are built with a very large resistance so that almost no current actually flows through the voltmeter itself. So it just senses the potential difference without diverting like any real current away from the main current. So if you look at series and parallel circuits, that would help a lot of people. Series and parallel circuits. So just imagine your series and parallel circuits like this, right? So ohm meters, let's go into ohm meters. So they measure resistance directly. They're inserted around a resistive element, and unlike the last two, voltmeters and ammeters, they are self-powered, so they supply their own small test current and measure how the component responds. And so just like ammeters, they have negligible resistance, so they don't add extra resistance to whatever they're testing. So the pattern to remember is ammeters go in a series with tiny resistance, voltmeters go in a parallel with huge resistance, and ohm meters, they just power themselves. All right, so that is chapter 6 done on circuits. Then we can move on to waves and sound. Okay, so now we're going into waves and sound. Waves and sound was always interesting to me because it had to deal with kind of like music. So it relates to sound and music, how music is made. So if you play an instrument, you might be a little bit interested in a way. But a wave looks like this. So it looks like a sinusoidal wave. This is the wavelength. This is a trough. This is your amplitude. And so what is a wave? A wave in general is basically a way that energy travels through space without the material actually moving. So there's two different types of waves to classify. You have transverse waves, which have oscillation of the wave particles that move perpendicular to the direction of the wave propagation. So an example of a wave like that would be your light wave. For oscillations that are parallel to the direction would be sound. Sound is an example that is parallel direction of the wave propagation. So transverse waves versus longitudinal. I'm going to find a picture. So here we can see transverse waves versus longitudinal. Transverse waves versus longitudinal. So again, longitudinal is parallel. Transverse waves are moving perpendicular. So look at the way these waves are moving. See, particle movement in longitudinal is moving this way. It's like parallel, whereas transverse is moving up and down perpendicular. Okay. Great. So now we can go into some of the formulas and the basics to define a wave. All of this is better. I don't know why there's not a better image of all of this, because all of this could be shown with graphs. So you should learn this via graph. I'm going to find one. All right. So basically, you have all of these stuff that we're learning now on displacement, amplitude, wavelength, frequency, Angular frequency, it's not really going to be on the graph for this one. Period is going to be on the graph, and then all of these three about interference, constructive and deconstructive interference, can learn it using pictures instead, because it's better to learn wavelengths in that way. So, and the same thing goes for light and optics as well. So if you look at the graph, we have our amplitudes, right, which is the maximum displacement. So if you ever had to calculate it, it's maximum displacement from the 0 line here. So it's how far the wave swings from its resting point to its most extreme point. So that is the highest part of the wave, and you call that the crest. The lowest point of the wave are called troughs. Okay, and so displacement is how far a specific point on the waveform is from its normal resting position. In other words, its equilibrium at any given point. So it's a vector, right? So meaning it has both size and a direction. So positive and negative displacement. And so wavelength is the physical distance between two identical repeating points. So this crest and this crest, or this trough and this trough. So wavelength is equal to those points there. So that's wavelength. And you see this lambda, that's what the symbol that's used for wavelength. Frequency tells you how many cycles. So this is one cycle here, right? This is one cycle. And if I did that again, that's 2. And this is basically almost half. So I have 2.5 cycles here, basically. So frequency will tell you how many cycles of the wave can happen per second. So a higher frequency means you have more wave cycles. So it ends up looking like, I haven't used the whiteboard in a bit, but if you have a high frequency, it'll look like this. A low frequency will look like slow oscillations, very slow. So lower cycles per second, lower cycles per second. All right. And then what else do you have to know? Yeah, so that's related to angular frequency. Your normal frequency is related to angular frequency. I didn't learn this as much, but yeah. It measures the same basic thing, but it's expressed in radians per unit time instead of cycles per second. So it's just different, but it's a mathematical way of expressing the same thing. So the rate of oscillation, in other words. So frequency and angular frequency are just measuring the same thing. It's just different ways of expressing it. Period is the amount of time it takes to complete one full cycle. So that's the formula for that is period equals 1 over f. So remember, f is measured in hertz, by the way. So if I go back to the picture, a period would be one of these cycles. Where is it? Period is the time it takes to complete one full cycle. So this could be one full cycle. You can also do it by using the troughs. From here to here would be one full cycle. I like to do it from here to here, which is the 0 points, like that. And then it will repeat again, one period. So it's one repeating, one cycle, you can think of it as like one repeating unit. And so one period is the time it takes to complete that one repeating unit. So it's the inverse of frequency. So if something has a high frequency, then it's cycling very often, right? And then each individual cycle then must take a very short amount of time, giving it a short period. So period and frequencies are always opposite. All right, so now we can go into, where is the next one? I think that's good. Yeah, now we can go into constructive and deconstructive. Yeah, so basically, waves can interact with each other that form a resultant wave. So it's better again to see pictures of this. So constructive and deconstructive interference for waves. Okay, let's see if Google will load this. Okay, so let's say I'm adding 2 waves together. Okay, this picture is good. So let's say I add 2 waves together that have the same time and the same amplitude like this. It's going to increase the amplitude even more. So let's say this was 2 decibels high and this was 2. Then it would be 2 plus 2, and then you get a 4 over here. So it's adding things, summating it up. Whereas deconstructive interference, when these 2 waves add up together, the resulting wave will be a cancellation. So there won't be any sound. That's why sometimes we have noise canceling headphones and we say, oh, the wavelengths are phasing each other out. Yeah, they're canceling each other out because they're opposite to each other. So this plus this will create a flat line. So it's like -2 plus +2. What would that make? 0. So you get cancellation. Okay. So that's the better way of trying to understand constructive interference and deconstructive interference. So constructive, again, the amplitude of resultant wave is equal to the sum of amplitudes of the 2 interfering waves, and deconstructive interference is the difference in amplitude between the 2 interfering waves. All right. And then you also have partially deconstructive and constructive interference. So you don't get a total adding up or amplification, or you don't get a total cancellation, you get a partial, and that's what partial constructive and deconstructive is about. So it's like having this, but the resultant wave is not fully canceled or it's not fully amplified. It's a little bit of both. Okay, now we can get into traveling waves, standing waves, nodes, antinodes, and damping. Just give me a second. So a traveling wave is exactly what it sounds like, a wave where the points of the maximum and minimum are consistently shifting position as the waves physically move through space. And a standing wave is basically produced when 2 waves of the exact same frequency travel in opposite directions. So they occupy the same space and time and interfere with each other. So the resulting wave looks like it's not traveling at all. So I'll show a picture. instead. So here's a difference. So standing traveling wave propagates forward, crests and troughs moves continuously throughout space, transports energy and momentum across the path of the wave. But a standing wave appears stationary and the pattern does not move left or right. Energy is trapped in place with no energy transfer. So on a standing wave, there's points on the wave where there's zero oscillation, antinode and node. I don't know if the diagram's on here. Let me check. Oh yeah, it's right here. Here they are. So diagram's here, but I'm just going to show another one. So standing waves, right? So they have nodes and antinodes, and this is the whole wavelength. And so on the, let's do the antinodes first. So the points that oscillate with the maximum amplitude is where the antinode is. So for standing waves. So, and then for nodes is where it's at basically zero oscillation, and those are called nodes. So this is what's happening in the standing waves here. Resonance is the increase in amplitude that occurs when a periodic force is applied at an object's natural resonant frequency. So every material likes to resonate at a certain frequency. So for example, a triangle, like the instrument, if you tap on the triangle, if you tap on glass, right, it has a certain natural resonance that it likes, or a frequency that it kind of likes to be at, and that's what we call our natural resonant frequency. And so what happens there is there's an increase in amplitude of where that resonant frequency is. So damping is a decrease in amplitude caused by applied or non-conservative forces. So you can think of damping as like, oh, sound likes to dissipate as it moves through space. So damping of sound. So you could think of damping of sound as, look, this sound started really high and now it's diminishing. It's getting smaller and smaller as it goes, as time goes by. And then sound. All right, sound is going to be pretty quick. For sound is produced by mechanical disturbance of a material that creates an oscillation of the molecules in the material. So think about this. To produce a sound, we have to have some sort of turbulent airflow for that to occur. So in our body, we use like our tongues or mouth as ways to create turbulent airflow. And so remember, we already established that sound already travels through a longitudinal wave. So a chain of reaction of compressions and expansions passed on from molecule to molecule, and that's related to how sound will propagate. So sound can travel through solids, liquids, and gases, so any form of matter, but it absolutely cannot travel through a vacuum because there are no molecules there to pass it all. So think about being in space where space is just silent because there's no air or matter for that sound wave to go through. So sound has to go through some sort of medium. So within a medium, as density increases, speed of sound decreases. Okay, let's go into pitch. Pitch is just our perception of frequency. So if I said, oh, someone has a high pitch, that means I think their frequency is high, their sound frequency is high. If I said, oh, someone has a low pitch, their frequency, I think, is low. But frequency is an actual objective number that you can calculate, as we've discussed. Frequency has a formula. Doppler effect is where you have a phenomenon where, like, Doppler effect is a shift in the perceived frequency of a sound compared to the actual frequency of the emitted sound when the source of the sound and its detector are moving relative to one another. So basically, you can think of the Doppler effect as when the source and detector are moving toward each other, right? So the detector is the person who's listening, or the listener, right? So when the source and the listener are moving toward each other, the perceived frequency is higher than what's actually being emitted. So sound waves are essentially getting bunched up and compressed as the source rushes towards you. So more wave crests reach your ear each second than normal. But when you're moving away, what happens is the waves get stretched out, and so they spread further apart. So when you have a wider spread of a wavelength, lower frequencies naturally have longer wavelengths than higher frequencies, right? So this wavelength stretches very long, and so they say that when the waves are getting stretched out and spread further apart, there's fewer crests that reach you per second, and so you perceive something lower. So the pitch is lower. So remember, pitches are just a perception of frequency. So even though the frequency might be the same, our perception is lower for that. And this is the formula for the Doppler's effect, perceived frequency. So the apparent frequency can be higher or lower or equal to the emitted frequency when the two objects are moving in the same direction, depending on their relative speeds. So the formula for the perceived frequency equals the emitted frequency multiplied by a fraction involving the speed of sound plus or minus the detector's or the listener's velocity over the speed of sound plus or minus the source's velocity. So the trick to remembering which sign to use is that if you use the top sign, in each plus or minus when the source and the detector are moving toward each other, and you use the bottom sign. So the top sign is plus, and then for this the top sign is minus for the denominator, and you use that when they're moving toward each other, and if they're moving away from each other, then you use the bottom sign. Intensity describes how much energy a sound wave is actually delivering, and is directly related to the wave's amplitude. So a bigger amplitude means a more intense sound. So intensity is equal to this here, power over area. All right, so intensity, so some real world examples, like intensity naturally decreases the farther you get from a sound source, since that same sound of power ends up spread over a larger and larger area as the sound spreads outward, and some of the sound's energy is also permanently lost along the way to something called attenuation, which is essentially friction like forces within the medium gradually absorbing and dissipating the wave's energy as heat. So that's kind of like an example for that. Then you have strings and open pipes. I don't know where closed pipe. Oh yeah, closed pipes is right there. So strings and open pipes and closed pipes. So for standing sound waves, this has to do with standing waves. And so this picture here are pictures of standing waves, and we already went over what nodes are and antinodes. So nodes were at zero displacement, so zero displacement, whereas antinodes are in maximum displacement. Maximum displacement there. So a string and pipes support standing waves, and the length of the string or pipe is equal to sum of the multiple lengths of half wavelengths. So that's the formula for that. Closed pipes are closed out. So just to show it a bit better, open pipes are literally what they say, they're open. The closed pipes are literally what they say, they're closed. So closed pipes, closed at one end, support standing waves, and the length of the pipe is equal to some odd multiple of quarter wavelengths. So that's that one. The formula for that. And then ultrasound uses high frequency sound waves to compare the relative densities of our tissues in the body. So the Doppler ultrasound is used to determine the flow of blood within the body. So yeah, that's it for sound waves. Doing lots of practice on this will help a lot, especially for understanding so by the way, N would be the harmonics down here. So first, second, third harmonics of a string. N is equal to node, A is equal to antinode, but this little n refers to what harmonic you're looking at. So are you looking at the first harmonic, second, or third harmonic? And so if you have a third harmonic, it's 3 times the wavelength divided by 2 in an open pipe. So I'll just show quickly open versus closed pipe as well before I end. Open versus closed pipe. So here you go. So these are examples of the open pipe, and this is closed pipe. So closed pipe, I accidentally drew it wrong, by the way. Closed pipe looks like this, but an open pipe is completely open on both sides, like this. Yeah, and they have standing waves in them. Okay, so that should be good. And then the next thing we'll be doing is light and optics, and lastly the atomic nuclear stuff. Okay, so now we're on the chapter 8 on light and optics. So we have the we're going to start with the electromagnetic spectrum. So electromagnetic waves are transverse waves. We learned about transverse waves over here, where we saw that light are transverse waves that have oscillations that are perpendicular to the wave thing. So wave propagation. So transverse waves that consist oscillating electric field and oscillating magnetic field. So the two fields are perpendicular to each other and to the direction of the propagation of the wave. So that is essentially what electromagnetic waves are. What else do you need to know? Yeah, and then for electromagnetic spectrum, it's the range of frequencies and wavelengths found in electromagnetic waves. So the EM spectrum looks like this. It doesn't look that great on here, but if I go to light mode, it might be easier to read it. So you have your full spectrum chart, which is visible light, so the stuff your eye can actually detect is over here. And then you have wavelengths that you can't really see, such as radio, microwave, infrared, ultraviolet, X-ray, and then gamma ray. So if you need to memorize, like, oh, if I have a gamma ray, then I'll have a shorter wavelength, higher frequency, and higher energy that moves on this side. Whereas if I go on this side, I have a longer wavelength, lower frequency, and lower energy. So one important note that it talks about here is that you note that gamma rays, X-rays, and higher energy end of the ultraviolet light are all ionizing radiation, meaning they carry enough energy to actually knock electrons loose from their nearby atoms, creating unstable free radicals. So free radicals form from this, and this is exactly why you have to wear a lead apron when dentists during an X-ray do X-rays, and why too much UV exposure from the sun can damage your skin cells, because that radiation has enough power to disrupt your actual molecules, so create free radicals. So yeah, your visible light spectrum, you gotta kind of memorize this, that that I think they put it in the essential equations somewhere. Where's the essential equations? Let me go find that. Essential equations, visible spectrum, wavelength. So red is 700 nanometers and 400 nanometers for violet. So if you go back to light and optics, you kind of have to memorize 700 and then 400 for violet or purple. That's important to remember. And then you have And then you have the hydrospectral series, which is over here. So for the hydrospectral series, it's basically when hydrogen atoms absorb or emit light. That light comes out in specific discrete discrete series, which each are tied to which energy level the electron is jumping to or from. So the Lyman series lands in ultraviolet and corresponds to transitions ending at the first energy level. The Balmer series, as it says here, Balmer lands in a visible light corresponding to the second energy level, and the Paschen series lands in infrared corresponding to the third energy level. So if you don't know this, it's important to review back to Gen Chem on, I think it's on even like chapter 1, I think, for Gen Chem. Love's beer pong is a way to help you memorize the hydrogen spectral series. And lastly, this Reinberg formula here lets you calculate the exact energy. This is related to chemistry as well. Exact energy and therefore the exact frequency of light released or absorbed when the electron jumps between the energy levels. So the idea is that the bigger the jump between energy levels, the more energetic, and the higher frequency resulting in the light that comes out of it. So let's go into geometric optics. So let's go into reflection first. So this is the basics. So reflection is rebounding of incident light waves at a medium's boundary. So basically the law of reflection is a simple rule where the angle at which the light comes in is the angle of incidence. So this is the angle of incidence here. And then the angle of reflection is right here. And then your normal is always the halfway between them kind of thing. So the normal is kind of like an imaginary line that's perpendicular to the reflecting surface. So here's the surface, which is the mirror. And so for spherical mirrors, let's see what else we have here. Yeah, spherical mirrors, curved mirrors are interesting because they result in different things. So this is more for flat mirrors, the law of reflection. But for spherical mirrors, a concave mirror curves inward, kind of like a spoon, so like this. So this is the example of a concave mirror in this picture here. And then a convex mirror kind of curves outward like this. And so these two images try to show you what's happening down. They try to show what's happening. So basically, in a concave mirror that's pointing inward, it produces an image, but that depends on where you place the object relative to something called the mirror's focal length. So you have a focal length. And so if the object sits farther from the mirror than the focal length, the mirror produces a real inverted image, meaning the real inverted image means that the image is flipped upside down and it's real because light rays will actually converge there and could be projected onto a screen. But if the object sits closer to the mirror than the focal length, here it produces a virtual upright. So virtual meaning the light rays only appear to come from that location, but they actually in real life don't converge there. So you need to look into the mirror to be able to see it. And it stays right side up, so that's why it says upright. For a convex mirror, which is over here, there's two situations. So convex, there's only one situation for convex here. So convex, it produces virtual, upright, and smaller. So what it means here is that convex mirrors always produce a virtual, upright, and smaller image, so no matter where the object is placed. This is exactly why those safety mirrors let you see a wide area, but it's just shrunken down. And a plain flat mirror that we're looking at always produces virtual, upright, and same size. So you can think of these as spherical mirrors, but with infinite radii of curvature. So basically, flat and curved mirrors aren't really two separate categories. Flat can be taken as like just the curved mirror, but to an extreme where it has an uncurved limit. And yeah, so you just kind of have to memorize that, really. And then after that is refraction. So you've probably seen this before when you place glass, like a straw into a glass of water, and it looks like the straw is kind of bending. And so that's refraction, the bending of light as it passes from one medium to another. So that's a definition. So why does this happen? It's because the speed of light actually travels at different speeds through different mediums or materials. And so when a wave changes speed while crossing a boundary at an angle, it bends. And that's the whole story behind refraction. So you can actually use a formula to measure the index of refraction, which is equal to speed of light in a vacuum divided by speed of light in the medium. So that's refraction. And then dispersion happens when different wavelengths of light separate from each other. So for example, when you have different wavelengths of light, that means you have different colors. So different colors get refracted by slightly different amounts as they pass through material, because a material's index of refraction depends a bit on their wavelength. And that's exactly why like a prism would split a white light into a full rainbow, because each color bends by a slightly different amount, which fans them apart. So if you've seen the prism, Snell's law is the law of refraction. So it's just a mathematical way of like calculating refraction, basically. So it's basically showing that there's an inverse relationship between the medium's index of refraction and the sign of the angle of refraction that light takes inside of it. So light bends essentially more sharply than the normal line when it enters a medium with a higher index of refraction. So higher index of refraction. So your total internal reflection here is basically you can think of it when light cannot be refracted on a medium as instead reflected back into the medium. So it occurs when light from a medium has a higher index of refraction to the medium with lower index of refraction with a high incident angle. So there's a specific angle called the critical angle, which is the minimum angle of incidence at which this total internal reflection will be able to kick in. So anything below that angle, light will still partially exit normally, but at or above that angle, 100% of the light will bounce back inside. So that's a critical angle here. What else is there? Critical angle. And then you have lenses. So you can think of lenses as like glasses and stuff like that. So lenses work by having refraction. So they refract light to form images of objects. And so they're bending light as it passes through a curved piece of transparent material to actually form images. And they follow a lot of the same real versus virtual logic that we saw with mirrors. So with convex lens, you get an image produced that's real, inverted, and the system is converging. So just like with the concave mirror, whether the resulting image is real or virtual depends on where the object is placed relative to the lens focal length. So an object farther than the focal length gives a real inverted image. Object closer to than the focal length gives a virtual upright image. And then for concave, so that's why you have these two scenarios that can happen with convex. And concave, you only have one where you have virtual upright diverging system. So regardless of where the object sits, similar to convex mirrors, they always behave the same way regardless of the object's placement, and the focal length itself relates directly to the physical curvature of the lens. Specifically, it's equal to half of the length's radius of curvature. So this is what it's showing here. F is half of R over here. And these are the images of the concave lens and the convex lens. So lastly, the lens maker equation here. For a perfectly thin lens, the simple focal length relationships above were great, but real lenses have real physical thickness, right? So once that thickness becomes significant, you need a more precise tool called the lens maker equation. And this formula will let you be able to calculate the lens's focal length based on its index of refraction and the curvature of each of its two surfaces, giving you an accurate answer even when the simplifying thin lens assumption starts to break down. So lenses with non-negligible thickness require this lens maker equation. Okay, so then we can go into diffraction, which is kind of like the opposite. So this is where light starts behaving in a way like a pond, or like a wave in a pond, rather than a straight line ray, right? So all of these rays are moving in straight lines. This is more diffraction is different. So diffraction is bending and spreading out of light waves as they squeeze through a narrow opening, so a narrow slit. Instead of just projecting a clean, sharp-edged beam straight through, the light fans outward, and especially when you add a lens to focus things, this can create like a bullseye pattern like this. Bullseye pattern, like that. So interference is like, so basically, yeah, the bullseye. One large, bright central band of light surrounded by alternating dimmer and brighter fringes on either side. So that's what it's saying here. And then interference is like when we covered waves in general. Whenever waves overlap, there's interference. So we already talked about it for waves over here. Interference. That was in the last chapter part. So I don't have to go over that again, I guess. And then Young's double slit experiment. So this is an experiment where light passes through two narrow, closely spaced parallel slits, and on the screen behind them. So this is on the screen behind them. How do I explain this? Instead of simply seeing two bright lines directly behind each slit, you see an entire pattern of alternating bright and dark stripes. So the bright stripes are called maxima, occur whenever the light waves from two slits are perfectly in phase and constructively interfere, and the dark strips are called minima. Minima dark fringes, bright fringes, maxima of intensity. So they occur, so your minima occur whenever they arrive perfectly out of phase and destructively cancel out. So remember what we learned about constructive and deconstructive interference of waves. So this experiment was powerful because it has evidence that light actually behaves as a wave. So this is important because it shows that the light goes through interference, and we know that's a property of what happens to waves with constructive and deconstructive interference. And then lastly, we have polarization. So for polarization, you just remembered that light's electric field oscillates in some direction perpendicular to its direction of travel. So in ordinary everyday light, let's say from a light bulb, that electric field is oscillating in every possible direction all at once randomly, and we call this unpolarized light. But when you have polarization, where you have polarized light, so here's our light bulb, and so typically it will oscillate normally in all these different directions, right? But when you have polarized light, it's where the electric field has been restricted to oscillate along just a single axis. So let's say it's up and down here, and you create this by passing a light through a polarizing filter, which you see here. polarizing filter only lets light through if the E field of the wave aligns with the openings in the filter. The E field of the existing light oscillate along the same axis. So you can see they're now oscillating along the same axis. And then there's also circular polarized light, which is a bit different. So every light ray has an electric field of the same intensity, but the field's direction is constantly rotating. So this is the image for that. It's constantly rotating in a direction as the wave travels forward, and it gives this spiraling pattern rather than staying fixed to one flat plane. So you produce circularly polarized light by passing ordinary unpolarized light through special pigments or filters, and that will introduce this rotating behavior, which is called circular polarized light. And lastly, there is the photoelectric effect. So I'll just do this in red. So the photoelectric effect is where you have it's simply the ejection, so the removal of an electron from the surface of a metal, and that's related to light, which is a great reason why we just went over light and optics. So if you didn't get light and optics from this one, then this one might be a little confusing. So the ejection of electron from the surface of metal in response to light. So energy of photon of light is E equals hf, and F is equal to, so you might see this formula as well, I think, which is hc over lambda, where F is equal to c over lambda, which is the speed of sound divided by the wavelength. So you might see that, and this would be general chemistry review. So that would be review for Gen Chem. And so to calculate from lambda from F, you would use this formula. So C is equal to F times lambda, so F times lambda is C. But if you wanted to do frequency, you would do C over lambda. Anyway, so the speed of light is always 3 times 10 to the 8, and the maximum kinetic energy in the photoelectric effect is K max equals HF minus work. And then that's it for that one. Threshold frequency is the minimal light frequency necessary to eject an electron from the given material, and then the work function is the minimum energy required to eject an electron from a given metal. And then Planck's constant, you just have to memorize 6.6 times 10 to the negative 34. And then after that, we can go over absorption and emission of light. So this is also Gen Chem review pretty much for the Bohr's model, but the Bohr's model states that you have the nucleus, and then you have around it the orbitals, so n equals 1, 2, 3, and so on. You can go out more, so you have those energy levels that are stable and discrete corresponding to specific orbits. And so absorption is when an electron can jump from lower energy to a higher energy orbit by absorbing a photon of light of the same frequency and the energy as the energy difference between orbits. And then emission is when the electron falls from higher to a lower energy. So this is essentially absorption is essentially turning the state of the electron from excited state would be absorption, and then ground state would be emission. So I can find a picture of ground versus excited state. Yeah, so ground state is being at the lower energy level, and then excited state is moving from low to high energy level, and these are all Bohr models. In other words, you see this diagram is called a Bohr model. Yeah, that's why Bohr models is introduced there. And then absorption spectrum may be impacted by small changes in molecular structure. So the absorption spectrum is a specific pattern of frequencies a given substance will absorb. So, and this pattern can shift subtly based on changes in molecule structure, basically. So it won't absorb everything. It's going to be a little bit specific, right? Fluorescence occurs when species absorbs high-frequency light and then returns to ground state in multiple steps. Each step has less energy than absorbed light and is within the visible range. So, yeah, so if you've ever seen something glowing and stuff like that, fluorescent materials appear to glow with visible color. So that's fluorescence. All right, so the next thing we're going to go into now is nuclear binding and mass defect. So for nuclear binding, it's the amount of energy that is released when nucleons, which are protons and neutrons, bind together. So remember, you have a nucleus of the atom. Yeah, the nucleus holds protons and neutrons, and so they're called nucleons. So both of them combined are called nucleons. And the nuclear binding energy is the amount of energy that's released when they bind together. So the four fundamental forces of nature: strong and weak nuclear force, electrostatic forces, and gravitation. So for the four forces, it's the strong nuclear force, the weak nuclear force. So those are two of them already. And then electrostatic is another one, so that's your third one. And the fourth one is gravitation. So you can think of electrostatic also as electromagnetic forces and gravitation. So the strong force is specifically what overcomes the natural electrostatic repulsion between positively charged protons crammed close together in a nucleus, holding the whole thing together against its own internal repulsion. So, yeah. So, for example, we know that nuclear binding energy is the amount of energy that gets released when an individual nucleons bind together to form a nucleus. So, there's this fact where the combined mass the combined mass of the nucleus's protons and neutrons, or the nucleons in other words, once they've actually been bound together and stuff, it's slightly less than the sum of their masses if you weight them individually, and that's mass defect. So they're completely separated from each other, and that missing bit, yeah, is called mass defect. Okay, so now we have nuclear reactions. So in nuclear reactions, there's fusion and fission. So fusion occurs when small nuclei combine into larger, fission splits into smaller nuclei. So for radioactive decay, so energy is released in both fusion and fission, so release of energy, because the nuclei formed in both processes are more stable than the starting nuclei. So for radioactive decay, basically, it's a spontaneous loss of the particles, from any unstable nucleus as this works its way toward becoming more stable. And so there are several distinct types, and each one changes the nucleus's mass number and charge, which is its atomic number, in a specific and predictable way. So we have here like alpha decay, beta minus, beta positive, and then we have the gamma decay. So radioactive decay, these are the types, right? Alpha decay, beta negative decay, I just circled those, beta positive decay, and then gamma decay. So right, in alpha decay, it involves the emission of an alpha particle, which is a helium nucleus, and it's made of 2 protons and 2 neutrons bundled together. All right, so since this ejects both protons and neutrons, the resulting nucleuses lose 4 units of mass number and 2 units of atomic number charge. So that's how you can predict for alpha decay. And then for beta decay, beta negative specifically, when a neutron is inside the nucleus, it transforms into a proton. So it splits out an electron and nearly, basically an undetectable particle called an antineutrino in the process. And since a neutron became a proton, the mass number stays exactly the same. So you still have the same total count of protons plus neutrons, but the atomic charge goes up by 1 since you gained a proton. So that's what happens there. And then for beta positive, also known as positron emission, is essentially similar. Proton transforms, it's not similar, it's like the opposite. A proton transforms into a neutron, releasing a positron instead. And basically, a positron is a positively charged version of an electron, and also releases a neutrino. So the mass number again stays the same, but this time the atomic number goes down by 1 since you lost a proton. So this is lost proton, so down and then up for gain proton. Okay, and then gamma decay is different from others. It doesn't actually change the composition of the nucleus at all, but it can still happen. So instead, it simply releases a high energy photon, which is a gamma ray, as a nucleus that's sitting in an excited high energy state, and it will settle down into a calmer, more stable configuration. And since no protons or neutrons are gained or lost, both the mass and atomic numbers stay constant. So it doesn't change at all. And then we have electron capture. So it's for this process, instead of the particle being ejected, the nucleus actually absorbs an electron. So it absorbs an electron from one of the atom's own inner electron shells, and that captured electron combines with the proton inside the nucleus to form a new neutron. So the mass number stays the same, but the atomic number goes down by 1. By the way, the mass is A in this one, and the atomic number is Z, the one at the bottom. Knowing how to read this is important too. Okay, half-life and exponential decay. So these are related. And important. And then this is a summary chart of everything we went over. It's a nice chart too. For half-life and exponential decay, so basically radioactive decay doesn't happen at a fixed predictable amount for any single nucleus. It's fundamentally random for any individual atom, but across a large sample of radioactive atoms, you can figure out like decay. And so decay is like a reliable statistical pattern to figure out, it started from here and now it's gonna go down, right? And so you need a large sample for that, and decay follows that pattern, described by something which we call half-life. So half-life is the amount of time it takes for exactly half of a radioactive sample to decay away. So half the time it takes for a radioactive sample to decay away. Equivalently, you can say it's the time it takes for the sample's overall radioactivity to drop to half of where it started at. So that's basically what it's saying here about the half-life. For exponential decay, we're looking at these equation, this equation here. So n equals n0 e to power negative lambda t. So the key insight about half-life is that it will always stay constant no matter how much material you started with. If a substance has a half-life of a year, for example, then after 1 year, half of it is gone. If a substance has a half-life after, if the same substance that had a half-life of 1 year then after 2 years, what would happen? It would have 2 full half-lives. So that means you're left with a quarter of the original amount. And so after 3 half-lives, you're left with 1/8, right? So it keeps cutting itself and decaying, like exponentially decaying like that. That's what the exponential decay looks like there. I can draw it a little bit better probably, like that, the exponential decay downward. And so that is what we call exponential decay, basically. The amount of remaining follows through this curve, where the rate at which the nuclei decay at any given moment is directly proportional to however many undecayed nuclei are still left in the moment. So that's what this equation kind of shows you. Note, if the problem just says beta, they just mean beta negative. This is an important problem solving note. So you can think of beta negative as the default beta. So beta, when someone just says beta, it means like beta negative rather than beta positive. So that's it. That's everything. All right. I hope that was helpful.